The Sun, the central star of our planetary system, is a sphere of plasma in constant transformation, where unimaginable forces balance each other to sustain both its own stability and life on Earth. To understand how solar storms, auroras, and the phenomena that mark the current solar cycle 25 emerge, it is first necessary to dive into the anatomy of the star. The Sun is not a solid body, but a stratified structure composed of different layers, each with specific functions, colossal pressures, and temperatures that defy imagination. At the center lies the core, the true powerhouse that has kept the star shining for billions of years. There, nuclear fusion occurs, where hydrogen nuclei combine to form helium, releasing immense amounts of energy in the form of radiation. Temperatures in the core reach values close to 15 million degrees Celsius, and the density is so extreme that a simple cube of material from this region would weigh hundreds of tons on the Earth's surface. As the energy generated in the core propagates outward, it crosses the so-called radiative zone. This region works as an ocean of photons in which particles of light are emitted, absorbed, and re-emitted countless times before they manage to escape. The process is so slow and chaotic that the energy released in the core may take tens of thousands of years to pass through this barrier. Only after this journey does the radiation reach the convective zone, the layer where movements similar to boiling bubbles dominate. In this region, columns of heated plasma rise toward the surface, partially cool, and then descend again in a continuous cycle. This convection mechanism is crucial for the emergence of magnetic structures and for the variability observed in solar activity. It is also at this stage that the Sun's magnetic field originates, the result of dynamic processes known as the dynamo effect, which transform kinetic energy into magnetic energy. Arriving at the visible surface, we find the photosphere, the layer that our eyes perceive when we look at the Sun. Its thickness is relatively small compared to the size of the star, but it plays an essential role, as it is the point of transition between the turbulent interior and the external atmosphere. The photosphere has an average temperature of about 5,500 degrees Celsius and shows impressive details when observed with solar telescopes. Brighter regions called granules, which reflect convective movements, and sunspots, temporarily darker areas formed by intense magnetic fields that partially block convection and reduce energy emission locally. These spots are windows into the Sun's magnetic activity and are directly linked to the solar storms that we will later discuss. Above the photosphere lies the chromosphere, a thinner and less bright layer, but highly dynamic. It reveals itself during total solar eclipses as a reddish ring around the Moon, and its characteristic color is mainly due to hydrogen emission. In the chromosphere, the temperature rises again, contradicting the logic of progressive cooling as we move away from the core. This anomalous heating is still the subject of intense study, but it is believed that magnetic shock waves and reconnection processes play a fundamental role. Phenomena such as spicules, jets of plasma that rise like needles into space, give an idea of the intensity of this region. Finally, we reach the solar corona, the outermost and most impressive layer of the Sun's atmosphere. Invisible most of the time, the corona becomes visible during total eclipses as a white, diffuse halo extending for millions of kilometers into space. Temperatures in the corona exceed 1 million degrees Celsius, much higher than those recorded in the photosphere, representing one of the great enigmas of modern astrophysics. It is in the corona that the solar wind originates, a constant flow of charged particles traveling throughout the planetary system, shaping the space environment and interacting with planets, moons, and magnetic fields. This layer is also the stage for coronal mass ejections, gigantic explosions of plasma and magnetic fields that can reach Earth and trigger geomagnetic storms. Thus, when we observe the Sun as a whole, we realize that each layer plays a vital role in the energetic and magnetic dance that defines its nature. From the core, where energy is born, to the corona, which releases particles into space, the star is an inexhaustible source of phenomena that directly influence terrestrial life. Understanding this anatomy is the first step toward comprehending why solar cycle 25, at its peak and subsequent final breath, is producing storms capable of generating auroras at low latitudes and challenging modern technology. Solar activity is not constant. Although the Sun shines in a relatively stable way to sustain life on Earth, Its surface and magnetic fields are in constant change, following a rhythmic pattern already identified by science, the solar cycle. This cycle lasts on average 11 years, during which the number of sunspots, magnetic storms, and coronal mass ejections increases and decreases in a predictable way. In other words, the Sun breathes in pulses of activity, alternating periods of greater turbulence with phases of relative calm. This behavior has been monitored for centuries, and its understanding is essential to predict impacts on space weather and human technologies. The official counting of these cycles began in the 18th century, when astronomers started systematically cataloguing the number of sunspots observed daily. Thus, each cycle was numbered, from the first to the current cycle 25, allowing scientists to follow long-term trends and compare different periods of solar activity. Solar Cycle 1 was established based on records dating back to the year 1755. Since then, each new cycle is identified when solar activity reaches its minimum, that is, when the number of visible spots falls to almost zero. From that point, a growth phase begins until the maximum, when hundreds of spots can be seen, and then it declines again until the next minimum. This pattern, although relatively regular, is not perfect. Some cycles last only 9 years, while others stretch to 14. Some are intense, full of storms and explosions, while others pass almost unnoticed. This irregularity shows that the solar dynamo, the internal mechanism that generates magnetic fields, is a complex process and not yet fully understood. An important milestone in the history of solar cycles was the identification of the so-called Maunder minimum, which occurred between the years 1645 and 1715. During this period, sunspots practically disappeared for decades, coinciding with the so-called Little Ice Age in Europe, when harsh winters and poor harvests marked the continent. Although the relationship between solar activity and the Earth's climate is still a matter of debate, the episode showed that prolonged variations in the sun's behavior can have global effects. Other similar periods, such as the Dalton minimum between 1796 and 1820, reinforce this historical correlation between solar cycles and climatic events. With the advancement of science in the following centuries, the observation of sunspots ceased to be only visual and gained support from photographic instruments, spectroscopic analysis, and more recently, space probes. This made it possible to refine historical data and expand the understanding of the evolution of the cycles. Today, when analyzing the series of 25 officially recorded cycles, it is evident that some stood out for their intensity. Cycle 19, for example, which occurred between 1954 and 1964, was the most active ever documented, with peaks of sunspots and geomagnetic storms that affected electrical systems and communications of the time. Cycle 24, which officially ended in December of 2019, was considered weak, with activity significantly below the historical average. The current solar cycle 25, which began in 2019, arose under great expectations. Initially, scientists believed it would be a cycle as weak as the previous one. However, as it progressed, it became evident that it was exceeding predictions. In 2023 and 2024, the number of sunspots was already much higher than projected, culminating in a solar maximum in mid-2025 that surprised even the most cautious specialists. This discrepancy between predictions and reality shows how the sun's behavior still challenges mathematical models and how space weather remains a field in constant learning. The importance of this historical count is not limited only to scientific curiosity. It provides fundamental parameters to assess the risks of solar storms and plan technological protection measures. By understanding how previous cycles behaved, we can compare the intensity of the present and estimate the chances of major events. Furthermore, historical analysis allows us to understand long-term patterns, such as periods of maximum activity alternating with phases of extended calm. The count up to cycle 25 is therefore more than a timeline. It is an indispensable tool to predict the future of space weather and to prepare humanity for possible technological catastrophes caused by the sun. When solar cycle 25 officially began at the end of the year 2019, expectations were that it would be modest, perhaps even weaker than cycle 24, which had disappointed observers due to its low intensity. Mathematical models developed by international teams of space weather specialists predicted a relatively small number of sunspots, a mild maximum in the middle of the decade of 2020, and activity comparable to a period of solar calm. These projections were based on historical series of previous cycles and on models that attempt to simulate the internal functioning of the solar dynamo, responsible for generating the magnetic fields that drive the entire activity of the star. However, throughout 2022 and 2023, the data began to contradict the forecasts. The sunspot count grew at an accelerated pace, geomagnetic storms became increasingly intense, and auroras were recorded at surprisingly low latitudes. This mismatch between theory and reality exposed the difficulty of accurately predicting the behavior of the sun. The solar dynamo is fueled by complex plasma movements in the convective zone, interactions of magnetic fields extending through the photosphere, and phenomena not yet fully understood in the corona. Small variations in any of these regions can drastically alter the cycle, making projections vulnerable to significant margins of error. Thus, while models suggested that cycle 25 would be calm, the sun showed that it still holds secrets, and that its internal processes partially escape our ability to predict. This unpredictability turned the cycle into a kind of cosmic surprise for the scientific community. In 2024, the contrast between expectation and reality became even more evident. During the first half of the year, intense auroras were recorded in countries of mid-latitudes and even in regions near the equator. Cities that had never witnessed this natural spectacle saw their skies filled with luminous curtains in green, purple, and red. The impact was so great that the search for northern lights reached record levels in Google Trends, reflecting global attention to the phenomenon. This wave of interest coincided with some of the strongest solar storms of recent decades, some of them classified at alert levels close to major historic storms, such as the Carrington event in 1859. For scientists, the unexpected performance of cycle 25 brought both concerns and opportunities. On one hand, it highlighted the risks of underestimating solar activity, as satellites, power grids, and communication systems were more exposed than predicted. On the other hand, it provided a natural laboratory of global-scale observation, allowing real-time study of rare phenomena that are valuable for understanding space weather. Satellites such as the Parker Solar Probe and the Solar Orbiter, which were on active missions, were able to collect precious data on the dynamics of the solar wind, plasma explosions, and the structure of the corona during moments of intense activity. These records became fundamental for adjusting theories and improving predictive models, although a long way still remains before solar storms can be forecast with the same precision as terrestrial weather. Another aspect that made cycle 25 remarkable was the way it reignited public interest in the sun. The popularization of auroras at low latitudes turned the phenomenon into a true cultural trend, inspiring trips, photography, live broadcasts, and global discussions. This engagement, combined with increased media coverage, highlighted the relevance of the subject not only as scientific curiosity, but also as an issue of planetary security. After all, if a major event were to hit Earth, the impacts on satellites, the internet, aviation, and power grids could be catastrophic. Therefore, solar cycle 25 surprised because it defied established forecasts, showed that models are still insufficient, placed space weather in the global spotlight, and reignited collective awareness that we live under the direct influence of a living and dynamic star. Instead of a discrete cycle, we witnessed an exuberant, turbulent cycle full of lessons, whose final breath still promises remarkable events before giving way to cycle 26. The year 2025 marks the culmination point of solar cycle 25, the so-called solar maximum. This moment is characterized by the largest number of visible sunspots, by the significant increase in eruptions, and by the intensification of the solar wind that continuously flows beyond the corona. It is a phase in which the sun seems to boil, revealing more clearly its nature as a magnetic star. When observed through telescopes equipped with special filters, The solar disk at maximum appears covered with dark spots, which are temporary regions of intense magnetic activity. These spots, which vary in size from small imperfections to areas capable of engulfing dozens of planets the size of Earth, are the visible face of magnetic structures so strong that they partially block the convection of energy in the photosphere. The greater the number of spots, the higher the probability of violent explosions known as flares and coronal mass ejections. During the solar maximum, the Sun's magnetic field lines become particularly unstable. They twist, tangle, and often reconnect, releasing energy at levels that defy any comparison with terrestrial phenomena. A single solar flare can release energy equivalent to billions of nuclear bombs exploding simultaneously. When these explosions are accompanied by coronal mass ejections, immense clouds of plasma are thrown into space at speeds exceeding 2,000 kilometers per second. If directed toward Earth, such ejections collide with the planet's magnetic field, triggering geomagnetic storms capable of generating auroras at low latitudes and interfering with satellites, communication systems, and even power grids. The indices that measure geomagnetic activity, such as the KP index, often reach high values during this phase, signaling that Earth is under the influence of large-scale storms. In May of 2024, for example, even before the official peak of the cycle, one of the largest solar storms of recent decades was recorded, with auroras visible in unusual regions such as Brazil, Mexico, and Spain. This episode anticipated what specialists expected for 2025, a succession of intense and continuous events that had already shown that the solar maximum of this cycle would be far more agitated than predicted. The year 2025, therefore, consolidated itself as a privileged observation point to study the relationship between the Sun and Earth's space weather. The solar maximum is also a moment when the very magnetic structure of the Sun undergoes a transformation. During this phase, the solar magnetic poles invert. In other words, the Sun's magnetic north pole switches places with the south pole. This phenomenon, which happens approximately every 11 years, is an essential part of the functioning of the solar dynamo and the renewal of its cycle. The magnetic inversion is gradual, taking a few months to complete, but it symbolically marks the heart of the solar maximum. It is as if the star resets its field lines, preparing itself to begin the descent toward the minimum that will close the cycle around the end of the decade of 2020. For the scientific community, the solar maximum of 2025 offers an unprecedented opportunity for observation, as different probes and telescopes are active simultaneously. Missions such as the Parker Solar Probe, which gets increasingly closer to the corona, and the Solar Orbiter, which captures images of the Sun's high latitudes, provide data never before available in previous cycles. These instruments allow for a more detailed understanding of how eruptions begin, how particles accelerate, and how the corona heats to temperatures above 1 million degrees Celsius. Such information is fundamental for improving predictive models and reducing risks to humanity's technological infrastructure. Thus, the solar maximum of 2025 is not just a statistical milestone within the count of solar cycles. It is the climax of a sequence that has been growing since 2019, a point where the Sun's magnetic activity reaches its most extreme expression, bringing both visual spectacle in the form of auroras and concrete dangers for satellites and power systems. It is the peak of the energetic dance of the star that sustains life, but that also tests the limits of human resilience in an era deeply dependent on technology. When we talk about solar maximum, many imagine that after this point, the Sun's activity simply begins to decline in a uniform and predictable way until the next minimum. However, reality is much more complex. After the peak of sunspots, flares, and coronal mass ejections, the Sun enters a phase informally known by scientists as the final breath of the cycle. This poetic expression describes a period that can last from 1 to 3 years after the official maximum, in which the star still presents bursts of intense activity, even while already in a trajectory of decline. It is a moment when large-scale geomagnetic storms may still occur, generating spectacular auroras and affecting terrestrial technologies. The final breath happens because the inversion of the solar magnetic poles, which takes place at the peak of the cycle, does not immediately end the instability. On the contrary, During this process of magnetic reorganization, the Sun still produces active regions, abundant sunspots and complex structures in the corona. This post-maximum turbulence is unpredictable and often deceives those who expect a quick return to calm. In some cycles, such as cycle 23, severe storms occurred years after the official maximum, showing that the decline does not mean the absence of risk. In cycle 25, which reached its peak in mid-2025, the prediction from international observatories is that this final breath will be especially agitated, extending until 2027 with events capable of surprising even the most cautious specialists. From Earth's perspective, this period is critical. Satellites orbiting at low and medium altitudes still face a high risk of damage caused by energetic particles, which can saturate their electronic systems and shorten their lifespan. Power grids remain vulnerable to geomagnetically induced currents capable of causing regional blackouts. Aircraft on polar routes still need to adapt their trajectories to avoid regions of higher radiation. In other words, the final breath keeps the planet on alert, requiring constant monitoring of space weather. A fascinating aspect of this phase is the occurrence of auroras at low latitudes. This happens because, even in decline, solar storms can still reach extreme levels, compressing Earth's magnetic field and allowing particles to penetrate regions close to the equator. This was the case in May of 2024, when auroras were seen in Brazil, Mexico, and even in countries in southern Europe. This type of event, once considered extremely rare, became more likely during the breath of cycle 25, fueling the cultural and scientific phenomenon that spread across the world. In addition, the final breath is a valuable opportunity for science. Unlike the beginning of a cycle, when activity is still low, this period offers the chance to study the decline in a controlled way and compare the intensity of storms with the conditions of the maximum. Ground-based telescopes and space probes use these years to collect valuable data on how the solar magnetic field reorganizes, how the corona dissipates energy, and how the star slowly transitions toward the next phase of calm. Each flare and each ejection observed at this stage help calibrate predictive models that, until today, still fail to anticipate the exact magnitude of events. The concept of final breath reminds us that the Sun does not obey our calendar or our linear expectations. It is a dynamic organism, governed by chaotic forces that manifest in waves of activity even after the maximum point. For humanity, this phase represents a mixture of beauty and risk, a spectacle of auroras that inspire millions of people, and at the same time, a constant threat to the foundations of technological civilization. In cycle 25, this combination of fascination and danger will be intensely experienced until the end of the decade, when the Sun will finally begin to fall asleep toward the next minimum. Sunspots are one of the most visible and intriguing manifestations of the Sun's activity. They appear as dark regions on the photosphere, the layer we see with the naked eye, and represent areas of extreme magnetic field concentration. The darker coloration does not mean an absence of light, but rather a less intense emission compared to the surrounding surface. While the photosphere generally reaches temperatures of approximately 5,500 degrees Celsius, the interior of a sunspot may be around 4,000 degrees Celsius. This temperature difference is enough for sunspots to stand out as cooler areas, although they are still hotter than any terrestrial surface. The origin of sunspots is closely linked to the Sun's magnetic dynamo. Convective movements in the upper zone of solar plasma cause magnetic fields to be constantly twisted, stretched, and reconnected. In certain regions, the intensity of the magnetic field becomes so high that it literally blocks the transport of heat by convection. This interruption creates areas of relative cooling, which appear as spots. That is why these regions are associated with highly complex and unstable magnetic field lines capable of storing enough energy to trigger colossal explosions such as solar flares and coronal mass ejections. The size of sunspots ranges from small structures resembling dark dots to gigantic formations, with diameters many times greater than that of Earth. During solar maximum periods, the number of spots can exceed hundreds, forming chains that span entire portions of the solar disk. These spots appear in pairs or groups, always associated with opposite magnetic polarities. This pattern reflects the geometry of the field lines that emerge and re-enter the solar surface, providing a dynamic portrait of the intense magnetic activity that reigns inside the star. Throughout history, the study of sunspots has played a crucial role in understanding the Sun. In the early 17th century, astronomers such as Galileo Galilei and Christoph Scheiner were the first to systematically observe them with telescopes, generating debates about their origin. At first, many believed they were planets transiting in front of the Sun, but it soon became clear that they were intrinsic phenomena of the star itself. Since then, continuous records have allowed the mapping of solar cycles and the recognition of the approximately 11-year regularity between maxima and minima. Sunspots, therefore, became not only objects of fascination, but also scientific tools for monitoring the pulse of the Sun. In recent times, detailed observation of sunspots has been enhanced by satellites, such as the Solar Dynamics Observatory and next-generation ground-based telescopes like the Daniel K. Inouye Solar Telescope in Hawaii. These instruments reveal the fine structure of sunspots, showing colossal-scale plasma granules, magnetic filaments, and penumbral regions that surround the darker core. The images make it possible not only to better understand the functioning of the solar magnetic field, but also to predict possible explosive events associated with these active regions. Sunspots are, in essence, windows into the magnetic heart of the Sun. Each of them signals accumulations of energy ready to be released in the form of flares or ejections. Thus, observing sunspots is not only contemplating the beauty of astrophysics in action, but also monitoring potential threats that may directly affect Earth. During Cycle 25, the unexpected growth in the number of spots demonstrated the vigor of the solar dynamo and announced storms capable of producing auroras visible far beyond polar regions. These dark regions are therefore both warning beacons and scientific wonders, reminding us that the surface of the Sun is far more dynamic than it might seem at first glance. Solar flares, also called solar eruptions, are one of the most impressive and energetic phenomena that the Sun can produce. They occur when highly stressed magnetic field lines in the solar atmosphere suddenly reconnect, releasing accumulated energy within minutes. This release can be compared to the simultaneous explosion of billions of nuclear bombs, radiating intense waves of radiation that travel through space almost instantly. The energy released by a single flare spreads across multiple wavelengths, ranging from radio to gamma rays, and reaches Earth in only 8 minutes, the time it takes for light to travel the distance between our planet and the Sun. From the observational point of view, solar flares are classified into different categories according to their intensity. The scale ranges from smaller classes, such as A and B, to the most powerful ones, known as Class X. Each increase in class represents a multiplication in the amount of energy released. A Class X flare, for example, is strong enough to interfere with radio communication systems, damage satellites in orbit, and even endanger the safety of astronauts on space missions. During Solar Cycle 25, Class X flares were recorded more frequently than expected, especially in the years 2024 and 2025, contributing to the wave of auroras observed at middle and low latitudes. An important aspect is that, unlike coronal mass ejections, flares do not carry large amounts of plasma toward Earth. They are basically pulses of electromagnetic radiation that spread through space at the speed of light. However, their effects are immediate. Within minutes, they can cause high-frequency radio blackouts over vast areas of the planet, mainly in regions facing the Sun at the moment of the eruption. In addition, these events energize particles in the solar wind, which can interact with Earth's magnetic field, intensifying geomagnetic storms when they coincide with associated coronal mass ejections. From the scientific point of view, solar flares are privileged windows into understanding the extreme physics of plasma. They reveal how magnetic energy can be converted into heat, radiation, and particle acceleration on scales that cannot be reproduced in terrestrial laboratories. Models of magnetic reconnection, developed by physicists throughout the 20th century, seek to explain the speed at which these eruptions occur and why the release of energy is so efficient. Space observatories such as the Solar Dynamics Observatory, GOES, and the Parker Solar Probe have recorded unprecedented details of these explosions, allowing researchers to map their evolution in real time and predict their impact on near-Earth space. Solar flares are also a constant reminder of the fragility of our technological infrastructure. A single event of great intensity can compromise navigation satellites, interrupt military and civilian communications, delay commercial flights, and even affect power grids. Although most flares primarily affect communication systems, risks increase when they are associated with coronal mass ejections, creating complete solar storms with far-reaching effects. This combination, more likely during the maximum and the final breath of cycle 25, is the reason why space weather specialists maintain continuous and real-time monitoring of the sun. Thus, solar flares are not only spectacles of cosmic energy, but also warning signs. They reveal the intensity of the sun's dynamism and test humanity's ability to coexist with a living star, whose eruptions have the power to alter the course of daily life on our planet. In cycle 25, their frequent occurrence showed that the sun is still capable of surprising us, reminding us that our dependence on technology makes us more vulnerable than ever to the whims of this colossal star. Among all solar phenomena, coronal mass ejections are among the most impactful and dangerous for Earth. Unlike flares, which are almost instantaneous bursts of radiation, coronal mass ejections consist of immense clouds of electrically charged plasma that are hurled into space from the solar corona. These eruptions involve billions of tons of particles, composed mainly of protons and electrons, accompanied by extremely intense magnetic fields that propagate through the planetary system. The speed of these clouds varies, but in extreme cases, it can exceed 2,000 kilometers per second, covering the distance between the Sun and Earth in just 1 to 3 days. When a coronal mass ejection is directed toward our planet, a dramatic process of interaction with Earth's magnetosphere begins, the invisible shield formed by the magnetic field that protects Earth from most of the solar wind. Upon striking this barrier, the solar plasma can compress and deform it, allowing the large-scale entry of energetic particles. This penetration fuels geomagnetic storms, phenomena capable of inducing electric currents in transmission networks, interfering with satellites, disorienting navigation systems, and triggering spectacular auroras at much lower latitudes than usual. The impact depends not only on the speed and density of the cloud, but also on the orientation of the solar magnetic field carried by the ejection. If this field is oriented opposite to that of Earth, the connection is more efficient and the effects are intensified. The history of coronal mass ejections shows that their effects can range from beautiful luminous spectacles to technological catastrophes. The most emblematic example was the Carrington event in 1859, when a colossal ejection struck Earth with enough force to cause auroras visible even in regions near the equator. Telegraph systems worldwide suffered overloads, sparks set papers on fire, and operators were electrocuted by induced currents. Another notorious case occurred in March 1989, when a geomagnetic storm caused by solar ejections collapsed the entire power grid of Quebec, Canada, leaving millions of people without electricity for hours. These episodes reinforce the destructive potential of ejections and explain why space agencies such as NASA and NOAA invest so many resources in continuous monitoring of the sun. During cycle 25, the frequency and intensity of coronal mass ejections increased significantly, especially in 2024 and 2025. Some reached Earth in just 36 hours after emission, causing auroras at low latitudes, temporary failures in radio communication systems, and the need to reroute flights to avoid polar regions. These events were accompanied by global geomagnetic storm alerts, keeping authorities and companies on alert. The phenomenon also fueled a cultural wave, as millions of people began following aurora forecast maps in real time, seeking to personally witness the celestial spectacle provided by these gigantic solar clouds. From a scientific point of view, coronal mass ejections represent a challenge. Despite advances with probes such as Solar Orbiter and Parker Solar Probe, it is still difficult to predict the trajectory and intensity of an ejection with precision. Many times, an eruption that appears visually impressive may not reach Earth, while others that seem modest may provoke severe storms when interacting in a specific way with Earth's magnetic field. This uncertainty makes space weather remain a developing scientific frontier, crucial for the protection of satellites, power grids, and communication systems. Coronal mass ejections are, in summary, powerful reminders of the direct connection between the Sun and Earth. Each cloud launched by the solar corona can turn into a luminous spectacle, or a real threat to global technological infrastructure. In the final breath of Cycle 25, several of these ejections are expected to still reach our planet, keeping alive the tension between wonder and risk, between beauty and vulnerability. It is in this delicate balance that humanity contemplates the sky and realizes that, despite all our technological progress, we remain deeply dependent on and exposed to the mood of a star 150 million kilometers away. The solar wind is one of the central elements in the relationship between the Sun and Earth. It consists of a continuous flow of charged particles, mainly protons and electrons, that escape from the solar corona and travel throughout the planetary system. This wind never ceases, even during periods of minimum solar activity, but its characteristics vary significantly depending on the star's conditions. Two of the most important variables are the speed and the density of the wind, factors that determine the intensity of its interactions with Earth's magnetic field, and consequently, the formation of geomagnetic storms. The faster and denser the solar wind, the greater the chances of disturbing the magnetosphere, inducing currents in power grids, and triggering auroras at low latitudes. The speed of the solar wind varies on average between 300 and 800 kilometers per second, but during coronal mass ejections, it can exceed 2,000 kilometers per second. This value is sufficient to cover the distance between the Sun and Earth in just 1 or 2 days, instead of the usual 4 or 5. The density of the solar wind, measured as the number of particles per cubic centimeter, also fluctuates intensely. In calm periods, this density may be close to 5 particles per cubic centimeter, but during extreme solar storms, it can reach values dozens of times higher. The combination of high density with high speed exponentially increases the impact of the wind on Earth's magnetic field. The effect of these variables becomes evident when analyzing historical storms. The Carrington event in 1859, for example, was fueled by an extremely fast and dense particle flow that struck Earth in less than a day. In the Quebec blackout of 1989, the combination of high density with a solar magnetic field oriented unfavorably generated induced currents that collapsed the region's entire electrical grid. These episodes demonstrate that it is not enough to observe only the occurrence of a solar ejection. The speed and density of the resulting wind are critical factors in determining the degree of danger. In the context of Cycle 25, the years 2024 and 2025 recorded multiple episodes of extremely fast and dense solar wind, provoking geomagnetic storms that surprised with their intensity. It was during such events that auroras were seen at unusual latitudes, from tropical countries to regions traditionally outside the auroral zones. In addition, satellites in low Earth orbit were forced to constantly adjust their positions, as the increase in particle density also generates greater drag on the upper atmosphere, expanded by heating caused by solar activity. This atmospheric expansion increases resistance on objects in orbit, shortening their lifespan and raising the risk of collisions with space debris. From a scientific point of view, monitoring the speed and density of the solar wind is one of the most critical tasks of space weather. Probes such as the Solar and Heliospheric Observatory and the Parker Solar Probe provide near real-time data, allowing for early warnings of geomagnetic storms. However, limitations remain. Even with advanced monitoring, it is often only possible to predict the intensity of a storm a few hours in advance when the plasma cloud is already close to Earth. This unpredictability reinforces the need to prepare critical infrastructures to withstand sudden surges, rather than depending solely on forecasts. The solar wind, in its speed and density, is the backbone of all space weather. It can be gentle and constant, ensuring the polar auroras that enchant travelers in the Arctic and Antarctic regions, or it can transform into a cosmic hurricane capable of challenging humanity's technological resilience. In the final breath of Cycle 25, when solar activity will remain elevated for a few more years, monitoring these variables will be essential to understand why auroras will continue to illuminate unlikely skies and why our power grids and communication systems will remain under constant threat. To understand the intensity of geomagnetic storms and communicate their risks clearly to the scientific community, monitoring agencies, and the public, a standardized scale known as the TKP index was created. This index measures the disturbance in Earth's magnetic field caused by interaction with the solar wind and coronal mass ejections. It ranges from 0 to 9 in whole numbers, with low values indicating calm conditions and high values reflecting severe storms. In essence, the KP index is the numerical translation of how strongly the Sun is shaking Earth's magnetosphere at a given moment. The calculation of the KP index is based on observations made by a global network of magnetometers, instruments capable of detecting the slightest variations in magnetic fields. These data, collected from different locations around the planet, are processed and converted into an average that represents the global state of geomagnetic activity. This standardization is essential, as it allows scientists, satellite operators, and even the general public to quickly understand the severity of the situation. A KP value of 2, for example, represents only minor variations, while a KP value of 7 already corresponds to a strong geomagnetic storm, capable of generating auroras at middle latitudes and causing problems in communication systems. The practical usefulness of the KP index is enormous. Airlines use this information to plan routes that avoid polar regions during periods of high activity, reducing exposure to radiation. Satellite operators adjust orbits and shut down sensitive systems to avoid permanent damage. Power grids prepare for surges of induced current that could compromise equipment. Even aurora observers, whether amateurs or professionals, rely on the KP index to know when and where they will have the chance to witness the phenomenon. For sky enthusiasts, KP values of 6 or more already indicate good chances of seeing auroras in regions far from the poles. A curious aspect is that the KP index has also become part of popular culture in recent years. Mobile applications, specialized websites, and live broadcasts began sharing real-time values, turning space weather monitoring into a daily activity for millions of people. In 2024 and 2025, when intense solar storms surprised the world, the number of searches related to the KP index skyrocketed. Ordinary people, without training in astronomy, learned to associate the value of this scale with the spectacle they could see in the sky. This popularization demonstrates how science and culture intertwine when cosmic phenomena become collective experiences. In solar cycle 25, the KP index was particularly useful in measuring the effects of storms that brought auroras to low latitudes. In May of 2024, for example, values reached KP8 during some episodes, which means a severe geomagnetic storm. These numbers, accompanied by spectacular images of the illuminated sky, went viral on social media and reinforced the public perception that we are living through a more intense and unpredictable solar cycle than imagined. Thus, the KP index is not just a technical metric. It is a bridge between the complexity of solar physics and the daily life of billions of people. By condensing scientific information into a simple and intuitive scale, it allows everyone, from engineers to photographers, to prepare for or marvel at the direct impact of the Sun on our planet. In the final breath of cycle 25, when new storms may still occur, this scale will continue to be one of the main thermometers for measuring the strength of the events that mark the turbulent relationship between Earth and its star. Polar auroras, known as the northern lights in the northern hemisphere and the southern lights in the southern hemisphere, are among the most beautiful and fascinating natural phenomena on the planet. They arise when charged particles from the solar wind collide with Earth's magnetosphere and are funneled along magnetic field lines toward the polar regions. These energetic particles, composed mainly of electrons and protons, penetrate the upper atmosphere, interacting with atoms and molecules of oxygen and nitrogen. The result of this interaction is the emission of light in different colors, spreading across the sky in curtains, arcs, and spirals of intense brightness. The physical process behind auroras is relatively well understood. When a coronal mass ejection or a stronger solar wind reaches Earth, part of the particles is deflected by the planet's natural magnetic shield. However, at the poles, where the magnetic field lines converge, these particles can penetrate more deeply into the atmosphere. When colliding with oxygen molecules at altitudes close to 200 kilometers, they produce the typical green light, the most common in auroras. Collisions at higher altitudes may generate reddish tones, while interactions with nitrogen molecules result in bluish or violet hues. This spectacle is, therefore, a visible reflection of the interaction between the Sun and Earth. a luminous dance that connects two cosmic realities. Auroras are normally restricted to the so-called auroral zones, located around 60 to 70 degrees of latitude, both north and south. In these regions, the phenomenon occurs almost daily, varying in intensity depending on the level of solar activity. Cities such as Tromsø in Norway or Yellowknife in Canada have become famous for offering visitors the chance to witness the spectacle frequently. However, during intense geomagnetic storms, these zones expand, allowing auroras to be seen much farther south or north than usual. This is precisely the phenomenon that gains prominence during stronger solar maxima, or in the final breath of turbulent cycles, such as the current cycle 25. Culturally, auroras have been interpreted in different ways throughout history. Nordic peoples associated them with divine manifestations or battles fought in the skies by the gods. In Japan, it was believed that children conceived under the glow of the aurora would be blessed with good fortune. Indigenous peoples of the Americas saw the lights as signs of ancestors or supernatural omens. These cultural readings reflect the profound emotional impact that auroras cause in those who observe them. Even today, in an era of advanced science, the spectacle continues to carry symbolism and a sense of direct connection with the mysteries of the cosmos. From a scientific and technological perspective, auroras also have practical importance. They function as natural indicators of the intensity of space weather. The stronger and broader the auroras are, the greater the energy penetrating Earth's atmosphere. For this reason, astronomers and space weather specialists closely monitor the occurrence of the phenomenon, associating it with solar storms and possible risks for satellites and power grids. The brightness of auroras is, in this sense, a visual translation of the sun's state and its interaction with our planet. In cycle 25, polar auroras ceased to be phenomena restricted to high latitudes and began to be seen in unprecedented places. In 2024, luminous curtains were recorded in low-latitude countries, surprising populations that had never witnessed the phenomenon. In 2025, new waves of storms brought auroras to tropical regions, turning the sky into the stage for a global spectacle. This expansion of the auroral zones was a direct result of the unusual strength of the solar storms of this cycle, marking one of the most extraordinary chapters in the recent history of astronomy and popular culture. Thus, polar auroras represent much more than a visual show. They are living proof of the intimate connection between the sun and Earth, a reminder that we live under the constant flow of energy from a star that, besides sustaining life, also challenges us with its strength and unpredictability. In the context of cycle 25, this phenomenon gained a new dimension, becoming simultaneously a scientific, cultural, and spiritual spectacle. Seeing an aurora in polar regions is already an extraordinary experience, but witnessing this phenomenon at low latitudes close to the equator is so rare that it becomes a historic event. The so-called low-latitude auroras occur only when geomagnetic storms of great intensity compress Earth's magnetosphere to the point of expanding the auroral zones beyond their traditional limits. On such occasions, cities that would never expect to see the sky painted in green, red, and violet are surprised by luminous curtains stretching across the horizon. This spectacle not only causes collective wonder, but also raises concern among scientists and authorities, as it indicates that the planet is being struck by an exceptionally powerful solar storm. From a physical standpoint, the explanation lies in how the solar wind and coronal mass ejections interact with Earth. Normally, Earth's magnetic field acts as a shield, deflecting most of the charged particles toward polar regions. However, when the flow is extremely strong and the orientation of the solar magnetic field is opposite to that of Earth's field, a more efficient magnetic connection occurs, allowing large amounts of energy to penetrate the magnetosphere. This process not only intensifies auroras in already known regions, but also expands their occurrence to middle latitudes and even tropical areas. In May 2024, for example, this mechanism caused auroras to be seen in countries such as Brazil, Mexico, and Spain, places where the phenomenon had never been recorded with such intensity. Historically, there are records of low-latitude auroras at different times. The Carrington event in 1859 brought visible lights as far as the Caribbean. Testimonies from the time describe skies so bright that people believed they were witnessing sunrise in the middle of the night. Another significant episode occurred in 1972 when intense solar storms produced auroras in parts of Vietnam and Hawaii. These reports became milestones in the history of space weather, reminding us that even in equatorial areas, Earth is not immune to the sun's whims. In solar cycle 25, auroras at low latitudes gained the status of a global cultural phenomenon. Images shared on social networks in 2024 went viral within hours, leading millions of people to go outside, hoping to see the colorful sky. This mass dissemination turned the phenomenon into a craze, placing it at the top of Google Trends searches. By 2025, new waves of storms reinforced this trend, with impressive records coming from tropical regions. For the first time, entire populations in areas far from the poles had direct contact with a phenomenon that, until then, seemed restricted to documentaries and trips to the Arctic or Antarctic. The implications of auroras at low latitudes go far beyond beauty. They serve as clear signs of solar storms of extreme magnitude, which can compromise essential technologies. Every time light curtains appear over the equator, there is elevated risk for satellites, power grids, and communication systems. Scientists therefore see these events as warnings that the sun is in a phase of exceptionally dangerous activity. For the public, however, the impact is mainly emotional and cultural, awakening feelings of admiration, collective unity, and even spirituality in the face of a spectacle that transcends borders. Thus, auroras at low latitudes represent a point of convergence between science, technology, and culture. They are at once indicators of risk, proof of the intensity of solar activity, and manifestations of beauty that reinforce humanity's perception of its cosmic vulnerability. In the final breath of cycle 25, the likelihood that this phenomenon will continue keeps the world in anticipation, ready to look up at the sky and witness once again the luminous dance of the sun in places where it once seemed impossible. Earth's magnetic field is one of the greatest gifts our planet offers to life. Invisible to our eyes but fundamental to our survival, it acts as a gigantic shield against the sun's constant fury. Formed by the movement of liquid metals in the outer core of Earth, mainly iron and nickel in a convective state, this field creates a protective bubble around the planet called the magnetosphere. Within this structure, a continuous battle is fought against the solar wind, an incessant flow of charged particles that travels through space at speeds ranging from hundreds to thousands of kilometers per second. Without this shield, Earth's atmosphere would be slowly eroded by the solar wind, as happened with Mars, and life as we know it would hardly have developed. The magnetosphere is not static. It expands and contracts depending on the intensity of the solar wind. On the side facing the sun, it is compressed, forming a barrier about 10 Earth radii away, while on the opposite side it stretches into a magnetic tail that can extend for hundreds of Earth radii into space. This dynamic structure ensures that most solar particles are deflected away from Earth. However, during intense geomagnetic storms, when coronal mass ejections strike the planet with high speed and density, the magnetosphere undergoes extreme compressions. Under such conditions, energetic particles can penetrate through the polar regions, feeding spectacular auroras and, in more severe cases, generating induced electrical currents capable of directly affecting human infrastructure. The importance of the magnetic field becomes even clearer when comparing Earth to other planets. Mars, for instance, does not possess a global magnetic field, only localized regions of residual magnetism in its crust. As a result, its solar wind interacts directly with the atmosphere, slowly stripping particles over billions of years and contributing to the arid and rarefied climate we know today. Jupiter, on the other hand, with a magnetic field dozens of times stronger than Earth's, has permanent and intense auroras, fueled not only by the solar wind, but also by the volcanic activity of its moon Io, which injects particles into Jupiter's magnetosphere. These examples show how the strength and structure of the magnetic field shape the destiny of each planet. From a technological standpoint, the protection offered by the magnetosphere is essential to keep our satellites, power grids, and communication systems functioning. When solar storms compress the magnetic field, satellites become more exposed to radiation and may suffer malfunctions or even permanent damage. The upper atmosphere itself, expanded by heating caused by the impact of the solar wind, increases drag on satellites in low orbit, shortening their lifespan. At the same time, induced currents in power grids on the ground can overload transformers and cause blackouts, as happened in Quebec in 1989. All this shows that the magnetosphere is not just an abstract shield, but a practical barrier that directly protects human civilization. In Cycle 25, the strength of the solar storms of 2024 and 2025 tested the limits of this protection. Auroras at low latitudes showed that the magnetosphere had been temporarily compressed drastically, allowing particles to penetrate regions of the planet usually untouched by such events. For scientists, this was a warning. Although Earth has an efficient shield, it is not impenetrable. The right conditions can expose significant vulnerabilities, reminding us that our safety depends on a delicate cosmic balance. Thus, Earth's magnetic field is much more than a scientific curiosity. It is the fundamental line of defense between life and the chaos of space. Thanks to it, we can exist in relative tranquility, even while orbiting a star capable of releasing enough energy to annihilate our technologies in an instant. In the context of Cycle 25, this reality became more evident than ever. While auroras amazed the world, Earth's invisible shield worked silently to ensure that the spectacle remained only a light show and not the harbinger of a global catastrophe. To understand the seriousness of the solar storms we are witnessing in Cycle 25, it is essential to revisit the history of two events that marked the relationship between the Sun and the Earth. The Pass-Carrington event in 1859 and the Palbam Quebec blackout pattern in 1989. These episodes not only reveal the destructive power of geomagnetic storms, but also show how our technological vulnerability has intensified over time. The Carrington event occurred on the 1st of September in 1859, when the British astronomer Richard Carrington was observing sunspots through a projection-designed telescope. That morning, he recorded an intense burst of white light, now identified as an extremely powerful solar flare. Less than 18 hours later, Earth was struck by an exceptionally fast coronal mass ejection, which compressed the magnetosphere and triggered one of the greatest geomagnetic storms in history. Auroras were seen in places so far from the poles that they illuminated skies in the Caribbean, in parts of Mexico, and even in northern Brazil. Reports from the time described lights so intense that people believed dawn had arrived in the middle of the night. The impacts were devastating for the technology available at the time. Telegraph networks on different continents collapsed, lines caught fire, papers ignited, and operators reported electrical shocks when trying to handle the equipment. In some cases, telegraph transmissions continued to work even after the systems had been disconnected from their batteries, powered only by the current induced by the geomagnetic storm. This episode showed early on the destructive potential that the Sun could exert over human electrical systems at a time when electrification was still in its infancy. More than a century later, on the 13th of March in 1989, another major event highlighted the risks of solar storms in an era already highly dependent on electricity. A coronal mass ejection struck Earth and provoked a geomagnetic storm classified as severe, lasting several hours. The result was a large-scale blackout in the province of Quebec, Canada. Induced currents overloaded transformers and brought down the entire power grid, leaving more than 6 million people without electricity for 9 hours in the middle of winter. The blackout caused disruptions to essential services, halted transport, and exposed the vulnerability of modern societies to space weather. Beyond the Quebec blackout, the same storm of 1989 generated spectacular auroras in low-latitude regions, including Texas and Florida in the United States. These episodes reinforced the alert for the scientific community and governments, showing that the threat is not only theoretical, but concrete and capable of generating billion-dollar losses in a matter of hours. Since then, agencies such as the National Oceanic and Atmospheric Administration of the United States and the European Space Agency have intensified monitoring of the Sun, creating dedicated forecasting centers for space weather. The contrast between Carrington in 1859 and Quebec in 1989 reveals something essential. The more technological a society is, the greater its vulnerability to solar storms. While in the 19th century the damage was limited to the telegraph system, by the end of the 20th century it was already impacting national power grids. Today, in the 21st century, with global dependence on the internet, communication satellites, navigation systems, and interconnected power grids, the effects of a similar event could be catastrophic, endangering not only economies but also daily life on a planetary scale. Thus, the memory of these two historical episodes is fundamental to understanding the current scenario. Cycle 25, with its unexpected intensity, has reignited fears of a new, modern Carrington. Each aurora seen at low latitudes, each failure in communication systems, and each geomagnetic storm alert reminds us that we live under the constant possibility that a solar event could transform, in a matter of hours, the way our civilization functions. The month of May 2024 entered history as one of the most extraordinary moments of aurora observation in the entire modern era. During this period, a sequence of solar storms struck Earth with unusual intensity, unleashing auroras that extended far beyond their usual latitudes. For the first time in generations, millions of people in low and mid-latitude countries, including Brazil, Mexico, and Spain, witnessed the night sky being overtaken by curtains of green, red, and violet lights. The spectacle, in addition to its cultural impact on the global population, served as a scientific warning that solar cycle 25 had reached a level of strength and unpredictability beyond what models had anticipated. The origin of this episode lay in a particularly fast and dense coronal mass ejection launched by the Sun at the beginning of May. This plasma cloud traveled the distance between the star and the Earth in only about 36 hours, colliding with the magnetosphere with an extremely unfavorable magnetic orientation. When the interplanetary magnetic field, carried by the ejection, is opposed to the Earth's magnetic field, the efficiency of the connection increases, allowing solar energy to penetrate with greater intensity. That was precisely the case here. The resulting geomagnetic storm was classified as severe, reaching levels near the maximum of the KP scale, and expanded the auroral oval to regions that would normally never be graced by the phenomenon. In Brazil, regions in the south and center-west registered auroras visible to the naked eye, an occurrence so rare that it stirred astonishment and prompted thousands of people to record images and videos. In Mexico, traditionally dark skies glowed with intense colors, drawing entire communities outdoors to observe the spectacle. In Spain, regions far from polar latitudes were also surprised by red curtains projected across the horizon, a phenomenon that quickly went viral on social media. International press coverage was immediate, with headlines emphasizing that the skies were being lit by one of the greatest space weather events of recent decades. From a scientific perspective, May 2024 represented a true natural laboratory. Monitoring stations scattered around the globe recorded in detail the evolution of the storm, enabling analysis of the velocity, density, and composition of the coronal mass ejection. Satellites such as GOES and the Solar Dynamics Observatory collected valuable data, confirming that this was one of the most intense events since the beginning of the space age. In addition to producing unforgettable auroras, the storm temporarily affected radio communication systems, required adjustments to low Earth orbit satellites, and forced airlines to alter routes in polar regions to reduce radiation exposure. Culturally, the impact was profound. Images of auroras in low-latitude countries dominated digital platforms, inspiring millions of people to research the sun, solar storms, and space weather. The term "northern lights" reached historic peaks on Google Trends, becoming one of the most popular searches of the period. This wave of interest demonstrated how a cosmic phenomenon, beyond being an object of scientific study, can also serve as a cultural and even spiritual catalyst. For many, witnessing the aurora in their own city was described as a transcendental experience, capable of evoking feelings of unity, awe, and reflection on humanity's place in the universe. The case of May 2024, therefore, was not only a luminous spectacle but a milestone that redefined the collective perception of the sun's power. It showed that auroras are no longer the exclusive privilege of travelers venturing into polar regions, but can appear unexpectedly in improbable places. At the same time, it served as a stark reminder that intense solar storms continue to be a real threat to technological civilization. In the final sigh of cycle 25, similar events may still occur, keeping the world on alert and in expectation before the unpredictable strength of our star. If May 2024 had already surprised the world with auroras at low latitudes, the year 2025 consolidated this new reality, bringing even more historic records in unexpected regions. As solar cycle 25 reached its maximum and advanced into the so-called final sigh, successive coronal mass ejections and intense geomagnetic storms continued to expand the auroral oval, illuminating skies over places where the presence of this phenomenon had never before been so clearly documented. For the first time, the world began to regard auroras not as a spectacle restricted to the Arctic and Antarctic, but as a global phenomenon capable of uniting people from different cultures in a single moment of wonder. Among the most striking records of 2025 were reports from African countries where observers managed to see faint but unmistakable green curtains on the horizon. In parts of tropical Asia, populations were also surprised by reddish hues in the sky, a phenomenon previously unimaginable at those latitudes. In South America, once again, auroras repeated themselves in regions of Brazil and Argentina, reinforcing the fact that the solar storms of cycle 25 were indeed exceptional. In southern Europe, areas of Italy, Greece and Portugal also recorded colorful skies, allowing millions of people to share simultaneously the same feeling of witnessing something historic. The cultural impact of these episodes was immense. Social media exploded with posts as videos and photographs circulated in real time and reached audiences who had never even heard of solar storms. The word aurora remained among the most searched terms on Google Trends throughout 2025, consolidating the phenomenon as part of the collective imagination. Television programs, documentaries, and live broadcasts began to include sections dedicated to aurora monitoring, turning space weather into a topic of daily interest for billions of people. What once seemed restricted to niches of scientists and travelers became a global cultural experience. From a scientific perspective, the events of 2025 were decisive in deepening the study of space weather. The geomagnetic storms that generated these auroras were accompanied by unprecedented data collected by probes such as the Parker Solar Probe and the Solar Orbiter. These instruments allowed the dynamics of coronal mass ejections to be observed at unprecedented proximity, revealing details about their velocity, density, and magnetic structure. The information obtained helped refine models that aim to predict the intensity and effects of such storms, although the margin of uncertainty remains high. The risks, however, were proportional to the beauty. On several occasions, communication satellites experienced temporary failures, global positioning systems displayed calculation errors, and airlines were forced to divert flights from polar routes to protect crews from radiation. These episodes made it clear that auroras appearing in unexpected places were not only spectacles but also direct consequences of solar events capable of profoundly affecting global technological infrastructure. The auroras of 2025 thus represented a milestone in the history of the relationship between the Sun and the Earth. They showed that we live in an era in which the effects of space weather have become tangible and routine for populations across the world. Each curtain of light in an improbable sky was at once a sign of vulnerability and a celebration, proof of the colossal strength of the star that sustains life, and a reminder that, even hundreds of millions of kilometers away, the Sun still dictates the rhythm of our civilization. The advance of humanity into a globally interconnected society depends to a large extent on satellites and radio communication systems that orbit silently above our heads. These devices enable the functioning of cell phones, televisions, navigation systems, military communications, and even the global internet. However, they all share a common vulnerability: direct exposure to space weather. When intense solar storms strike the Earth, highly energetic particles bombard the magnetosphere and cross its outer protective layers, reaching satellites in orbit. The result can range from temporary transmission failures to permanent damage to delicate electronic components. Radio signals are particularly sensitive to solar storms. During large magnitude eruptions, the ionosphere, the electrically charged layer of the atmosphere, undergoes drastic alterations. This layer is essential for the propagation of long-distance radio waves, as it reflects transmissions and directs them back to the Earth's surface. However, when energetic particles from the Sun saturate the ionosphere, this reflective capacity is compromised, resulting in communication blackouts. Airline pilots on long-distance routes, especially in polar regions, often face loss of contact with control towers during such events. In more severe storms, emergency radios and military services are also compromised, highlighting the fragility of telecommunications in the face of solar fury. In the case of satellites, the risks go beyond momentary interruption. High-energy particles can penetrate shielding and cause irreversible damage to electronic circuits. Onboard computer memories may be corrupted, solar panels may lose efficiency, and orientation systems may be temporarily or permanently affected. During intense geomagnetic storms, low Earth orbit satellites also face the aggravating factor of the upper atmosphere's expansion, which increases drag and accelerates their descent toward Earth. This forces operators to perform constant corrective maneuvers, raising costs and reducing the lifespan of equipment designed to last for decades. Recent events in Cycle 25 have confirmed these risks. In 2024, several companies reported instabilities in communication satellites right after severe geomagnetic storms. The global positioning system, used in critical applications such as maritime transport, precision agriculture, and emergency services, experienced deviations that compromised field operations. Satellite internet providers recorded temporary signal outages, and aviation radios experienced prolonged interruptions. These effects, even when short-lived, had significant economic impacts and reinforced the need for more advanced protection strategies. The vulnerability of modern telecommunications to space weather raises troubling questions about the resilience of our infrastructure. An event comparable to Carrington's, occurring in the 21st century, could disable much of the satellite fleet in orbit, globally compromising communications, navigation, and weather monitoring. To avoid a collapse of this magnitude, space agencies have been investing in more accurate forecasting systems and more robust shielding technologies. However, the unpredictability of solar events still places humanity in a position of dependence and risk. Thus, each aurora visible at low latitudes during Cycle 25 is not only a sign of beauty, but also a silent reminder that behind the dancing lights in the sky, the infrastructure that sustains our modern life is being tested. Satellites, radios, and global communication systems continue to operate in a fragile environment, subject to the whims of a star whose power can alter in an instant the functioning of our interconnected world. Among all modern infrastructures, few are as critical as power grids. They are the backbone of technological society, supporting everything from hospitals and transportation systems to the internet, food refrigeration, and industrial operations. Yet these same grids are among the most vulnerable to the effects of solar storms. During high-intensity events, energetic particles from coronal mass ejections can induce electric currents in transmission lines, turning kilometers of cables into true antennas that capture energy from space. The result can be devastating: transformer overloads, substation failures, and cascading collapses capable of provoking regional or even global blackouts. This risk is not just theoretical. On March 13, 1989, a geomagnetic storm brought down the power grid of Quebec in Canada, leaving more than 6 million people in the dark for 9 hours during a harsh winter. Currents induced by the storm burned transformers and damaged high-voltage lines, causing massive financial losses and exposing the fragility of modern energy infrastructures. If an event of that magnitude could collapse a grid in a time of lesser technological dependence, one can only imagine the impact of something even more intense today, in a world that relies on electricity for every detail of daily life. The greatest fear of specialists is the repetition of an event on the scale of Carrington in 1859, in the 21st century. In that episode, induced currents managed to set telegraph systems, the most advanced technology of the time, on fire. If something similar occurred today, high-power transformers could be destroyed on a large scale. The problem is that these components are not easily replaceable. Each transformer can take months or even years to manufacture, transport, and install. This means that a global blackout could last weeks or even months, compromising supply chains, water distribution, hospitals, and practically every basic function of civilization. In Cycle 25, the events of 2024 and 2025 demonstrated how modern grids remain exposed. Some geomagnetic storms caused instabilities in electrical systems of different countries, requiring emergency protocols to prevent larger collapses. In certain cases, power operators had to temporarily reduce the load on transmission lines to decrease the risk of failure. These episodes reinforce that, even with improved monitoring and defense protocols, grids remain in a vulnerable position against the power of the sun. Vulnerability becomes even more critical, given the growing interconnection of power grids on a continental scale. Today, systems from different countries are linked to optimize energy supply, but this interconnection also means that failures in one region can quickly propagate to others, creating cascading blackouts. This globalized risk demands new resilience strategies, such as installing more resistant transformers, blocking systems against induced currents, and international contingency plans. Thus, the auroras that enchant millions of people around the world are also warning signs. They show that high-magnitude solar storms remain active and that our civilization remains vulnerable. The final sigh of Cycle 25 may still bring events capable of testing the limits of global electrical infrastructure. If these risks materialize, we will not be facing only a spectacle of lights in the sky, but also a concrete threat to modern life. Protecting our power grids means protecting the foundation of all contemporary civilization, ensuring that the glow of auroras remains a spectacle and not the prelude to planetary darkness. If electricity is the heart of modern life, global positioning and satellite communication systems are its nervous system. They connect continents, guide transportation, regulate financial transactions, and provide essential services to billions of people every day. Yet, these systems are among the most sensitive to space weather. During intense solar storms, energetic particles and variations in the Earth's magnetic field directly affect the ionosphere, the electrically charged layer of the atmosphere that influences the propagation of radio and satellite signals. Any alteration in this layer can distort, delay, or even block signals that are fundamental for navigation, communication, and the synchronization of global networks. The Global Positioning System is a clear example of this vulnerability. Every GPS device depends on signals sent by a constellation of satellites orbiting the Earth at approximately 20,000 kilometers in altitude. These signals are extremely weak when they reach the surface, comparable to the power of a common light bulb observed from thousands of kilometers away. This means that any ionospheric disturbance triggered by a geomagnetic storm can alter the trajectory of the signal, causing location errors that range from a few meters to dozens of kilometers. For everyday applications, such as car navigation, this may seem only a nuisance. But for aviation systems, maritime transport, precision agriculture, and military operations, such errors can have serious consequences. Satellite internet, which gained global popularity through projects that launched thousands of small satellites into low Earth orbit, is also exposed to these risks. During severe solar storms, the density of the upper atmosphere increases due to heating, generating greater drag on these satellites and forcing them to carry out constant corrective maneuvers. In addition, magnetic interference can interrupt or temporarily degrade data transmission, leading to signal outages that directly affect millions of users. In rural and remote regions, where satellite internet is often the only option available, these interruptions can mean the loss of critical connectivity. Another sector highly dependent on the stability of satellite signals is that of global financial transactions. Banking systems, stock exchanges, and even power grids rely on satellite signals to maintain precise time synchronization. A delay of just a few microseconds can compromise financial operations, cause discrepancies in records, and even trigger failures in distribution chains. During recent solar storms, temporary deviations in timing systems were recorded, requiring emergency adjustments to prevent more serious problems. In Cycle 25, there have already been episodes that demonstrated how these risks can materialize. In May of 2024, significant location errors were reported in navigation systems across various regions of the world during geomagnetic storms. Aircraft had to adopt alternative protocols, and large ships reported temporary difficulties navigating in open seas. At the same time, satellite internet services experienced instabilities, with signal outages across several continents. These incidents, although brief, served as strong reminders that our dependence on satellites is total, and that any prolonged failure could generate social and economic impacts on a planetary scale. Thus, GPS, satellite internet, and navigation systems are not merely convenient tools, but the invisible pillars of modern life. Each aurora observed at low latitudes is also the reflection of a storm that threatens these crucial networks. In the final sigh of Cycle 25, we may still witness new episodes that will test the resilience of these technologies. Humanity's challenge will be to reinforce these infrastructures against the uncontrollable power of the sun, ensuring that connected civilization continues to function even amid the greatest cosmic storms. Over the past decades, the scientific community has worked hard to better understand the risks that solar storms represent for the Earth. Among the most active institutions in this field are the United States Space Agency, NASA, and the Space Weather Prediction Center of the National Oceanic and Atmospheric Administration, known as NOAA Space Weather Prediction Center. These entities maintain continuous monitoring of the sun, collecting real-time data and developing models capable of estimating the probability of major events, such as storms comparable to the Carrington event of 1859. The studies carried out are fundamental not only for science but also for the security of governments, telecommunications companies, energy providers, and even everyday users who depend on satellites and the internet. Reports from NASA and NOAA indicate that with each solar cycle, there is a significant probability of severe storms occurring. However, predicting exactly when and at what intensity they will happen remains a challenge. Scientists use a combination of direct observations made by satellites such as the Solar Dynamics Observatory and the Parker Solar Probe, along with mathematical models based on the physics of solar plasma. These models attempt to anticipate the behavior of sunspots, coronal mass ejections, and the solar wind, but the complexity of the star's magnetic dynamo still makes forecasting imprecise. On average, it is estimated that events comparable to Carrington could occur once every 100 to 200 years, but even this estimate is surrounded by uncertainty. An important aspect highlighted by these studies is that the intensity of solar storms does not follow a linear pattern. Some weak solar cycles may produce isolated extreme events, while stronger cycles may not generate equivalent episodes. This unpredictability reinforces the need for continuous preparedness. NOAA maintains alert scales that range from minor storms, with no significant impact, to the so-called G5 storms, classified as extreme, capable of severely affecting satellites, power grids, and communication systems. During Solar Cycle 25, alerts close to the maximum level have already been issued, showing that the threat is not distant, but very much present. NASA studies also emphasize the importance of space missions dedicated to space weather. The Parker Solar Probe, launched in 2018, is approaching closer and closer to the solar corona, collecting unprecedented data on the origin of the solar wind and on the processes that feed coronal mass ejections. Meanwhile, the Solar Orbiter, in partnership with the European Space Agency, provides high-resolution images and detailed measurements of the sun's magnetic activity. This information is essential to improve predictive models and reduce the margin of error in forecasts. Still, scientists acknowledge that we are far from having a fully reliable alert system comparable to terrestrial weather forecasting. The probability of major events is therefore not a matter of if, but of when. The scientific community already works with the scenario that severe solar storms will occur again at some point, and global preparedness is seen as indispensable. This includes protocols to protect satellites, shield power transformers, develop emergency communication systems, and educate the public about space weather risks. In Cycle 25, marked by stronger than expected storms, these alerts became even more relevant, showing that humanity must live with the reality that its star is both a source of life and a potential threat. Thus, NASA and NOAA studies on the probability of major events are not just technical records. They are a call to action, reminding governments and societies that the sun remains an unpredictable and powerful agent. In the final sigh of Cycle 25, the world remains on alert, aware that each aurora may only be a prelude to a storm with much greater consequences. The term space weather has become increasingly frequent in scientific and technological vocabulary, especially in recent decades. It refers to the set of dynamic conditions in space near the Earth, directly influenced by solar activity. Just as terrestrial weather depends on the interaction between the atmosphere, oceans, and air currents, space weather is shaped by the interaction between the Sun, its particle wind, the Earth's magnetic field, and the upper atmosphere. Understanding this relationship is essential, since the Sun, in addition to sustaining life with its light and heat, can also generate phenomena capable of drastically disturbing humanity's technological structures. The science of space weather began to take clearer shape with the space age in the 20th century. Before that, solar storms were only perceived indirectly, through auroras and failures in telegraph and electrical systems. It was only with the launch of satellites beyond the atmosphere that scientists were able to directly measure the solar wind, map energetic particles, and observe the dynamics of the solar corona in detail. Today we know that the Sun exerts a continuous impact on the surrounding space, creating a kind of cosmic weather that varies in intensity according to cycles of activity. This new science has become so relevant that institutions around the world have created research centers exclusively dedicated to monitoring and forecasting these phenomena. The relationship between the Sun and space weather is mediated mainly by the solar wind and coronal mass ejections. During periods of greater activity, the quantity of particles and energy released by the star increases, intensifying geomagnetic storms on Earth. This means that, just as meteorology predicts rain and atmospheric storms, the science of space weather seeks to predict solar storms. The difference lies in scale and complexity. While meteorological satellites can track clouds and cold fronts with great precision, predicting the behavior of a star is much more challenging due to the chaotic nature of plasma and the lack of complete data on the solar interior. In recent years, the field of space weather has grown significantly. Missions such as the Parker Solar Probe and the Solar Orbiter are providing unprecedented information about the physics of the corona and the origin of the solar wind. High-tech ground-based observatories such as the Daniel K. Inouye Solar Telescope in Hawaii capture images in impressive detail of sunspots and the star's dynamic surface. At the same time, space agencies such as NASA and NOAA, along with the European Space Agency and research centers in Asia, collaborate in global monitoring networks, cross-referencing data to improve forecast accuracy. This collective effort reflects the understanding that space weather is not just a scientific curiosity, but a matter of planetary security. From a cultural perspective, interest in space weather also exploded with the auroras of 2024 and 2025. The visual beauty of the phenomenon awakened popular interest in concepts once restricted to laboratories, such as the KP index, solar wind, and coronal mass ejections. Ordinary people, when following aurora maps on cell phone apps, began to consume space weather forecasts in real time. This popularization helped bring science and society closer together, showing that the Sun is not just a distant ball of fire, but a living force that directly influences modern life. The expansion of this science, however, still faces major challenges. Although it is possible to predict the occurrence of solar storms a few hours in advance, we still cannot accurately determine the intensity and duration of their impacts. Mathematical models advance with each cycle, but the unpredictable nature of the solar dynamo continues to impose limitations. For this reason, the study of space weather is considered an open frontier of astrophysics, with the potential for discoveries that may profoundly change our ability to protect civilization. Thus, the Sun and its relationship with space weather represent not only an emerging area of science, but also one of the most strategic for the future of humanity. In the final sigh of Cycle 25, the world finds itself at a unique point in history, where visible phenomena such as auroras walk side by side with invisible risks that can compromise power grids, satellites, and communications. Understanding this expanding relationship is therefore more than an academic matter. It is an essential step to ensure the resilience of modern life in the face of the uncontrollable power of our star. Imagining a new Carrington event in the 21st century is an exercise that combines science, forecasting, and even global survival scenarios. The storm of 1859 was recorded in an era when electrical technology was still in its infancy, limited mainly to telegraph lines. Even so, the impacts were impressive. Fires in telegraph stations, operators electrocuted, and auroras visible even in tropical regions. If an event of this magnitude were to occur today, the effects would be incomparably more devastating, given our absolute dependence on electricity, satellites, and interconnected digital systems. The first impact would be felt on satellites. Thousands of them orbit the Earth, responsible for communication, navigation, weather forecasting, and military monitoring. A massive flux of energetic particles could damage solar panels, corrupt electronic circuits, and even disable entire satellites. The consequence would be the immediate loss of global positioning signals, affecting aviation, maritime transport, precision agriculture, and emergency services. Satellite internet, which today connects millions of people, could suffer widespread blackouts. Without these services, global supply chains, e-commerce, and even financial systems would be deeply disrupted. At the same time, terrestrial power grids would suffer overloads caused by geomagnetically induced currents. High-power transformers could burn out in cascade, resulting in blackouts spanning entire countries. The major problem is that these components cannot be replaced quickly. Their manufacture may take months or even years. This means that some regions could remain without electricity for long periods. The impact on hospitals, water supply, public transport, and industries would be devastating. In an era where electricity sustains virtually all functions of society, a prolonged blackout would have catastrophic consequences for daily life. Another highly vulnerable sector would be aviation. During a superstorm, ionizing radiation increases significantly on polar routes, forcing aircraft to divert to safer regions, which raises costs and delays operations. In extreme cases, radio communications could be completely disrupted, leaving planes temporarily without contact with control towers. For passengers, this would mean mass delays and collapse in air transport systems. For the military, the loss of communication and precise navigation would represent a global strategic threat. Society would also face the collapse of global time synchronization. Financial transactions, stock exchanges, and even power grids depend on extremely precise signals sent by satellites to maintain synchronization at the microsecond level. Without this standard, there would be failures in banking records, errors in commercial transactions, and instability in international markets. Economic chaos could combine with technological chaos, amplifying the impact of the storm. Recent studies by NASA and NOAA indicate that there is a significant probability that events comparable to Carrington may occur at some point this century. Although the chances in a single year are small, the cumulative probability over decades makes the risk inevitable. This realization has led governments and companies to discuss resilience strategies, such as strengthening transformers against induced currents, developing more robust satellites, and creating contingency plans to maintain essential communications during major storms. If a Carrington-type event struck today, the impact would not be only technological, but also cultural and psychological. Entire populations would see the sky lit up by auroras never before imagined in their regions, a spectacle of beauty that would be both dazzling and apocalyptic. While millions of people admired the curtains of light, millions more would be in the dark, without electricity, communication, or access to basic services. This contrast between wonder and vulnerability would mark a planet confronted with the absolute power of its star. Thus, the hypothesis of a new supersolar storm is not science fiction but a possible reality. Cycle 25, with its intensity above expectations, reminds us that humanity needs to be prepared. If the Carrington event had occurred today, we would be facing one of the greatest challenges of modern civilization, a crisis capable of redefining our relationship with technology and with the sun itself. As humanity becomes increasingly dependent on satellites and sensitive electronic systems, the urgency to develop technologies capable of withstanding the impact of solar storms also grows. This need has given rise to a true technological race, involving space agencies, private companies, and military forces alike. The goal is to create more robust satellites, more resilient power grids, and defense protocols that can mitigate the effects of a storm comparable to the Carrington event. Solar Cycle 25, with its intensity surpassing expectations, has further accelerated this movement. placing space weather at the center of global security discussions. In the satellite sector, the first step has been to improve electronic design and shielding against radiation. Traditional semiconductor components are extremely vulnerable to energetic particles released during solar storms, which can cause failures or permanent destruction. To address this problem, engineers have been developing more resistant circuits, as well as redundant systems that allow a satellite to continue operating even if part of its components are compromised. Physical shielding with materials capable of absorbing ionizing radiation has also been enhanced, although there are limitations related to weight and cost. Another crucial point lies in the creation of automatic defense protocols. Many satellites are already programmed to enter safe mode when they detect a sudden increase in solar particles. In this state, non-essential operations are suspended, reducing the chance of severe failures. In addition, ground-based monitoring systems can send commands to temporarily shut down sensitive circuits before the storm reaches peak intensity. These protocols, however, rely on accurate forecasts, and this is precisely where the greatest challenges lie. Predicting in advance the arrival and exact impact of a solar storm is still extremely difficult. In the field of power grids, the technological race involves implementing transformers that are more resistant to geomagnetically induced currents and installing blocking devices to prevent these currents from propagating through transmission lines. Some nations are already testing selective shutdown systems capable of isolating critical regions of the electrical grid to avoid cascading collapses. In addition, contingency plans are being developed to ensure power supply in hospitals, military command centers, and emergency services, even in scenarios of prolonged blackouts. The military also plays an active role in this race. For armed forces, losing satellite communication or precise navigation during a solar storm can compromise entire strategies. For this reason, alternative navigation systems based on terrestrial signals are being developed, as well as experimental technologies that explore the use of Earth's magnetic field as a reference. The goal is to maintain sufficient redundancy so that critical operations are not paralyzed during extreme space weather events. The private sector, especially satellite internet and telecommunications companies, is also investing heavily in protection. Constellations launched into low Earth orbit must cope with increased atmospheric drag during solar storms, which requires more efficient propulsion systems for orbit corrections. In addition, companies are creating dynamic network management protocols, allowing services to be redirected from affected regions to more stable ones, thereby reducing disruptions for end users. However, despite these advances, the technological race remains uneven. Countries with greater investment capacity are better prepared, while developing nations remain highly vulnerable. This means that in the event of a global solar storm, the impacts would be felt disproportionately, exacerbating existing inequalities. Thus, the race for more resistant satellites and defense systems against solar storms is, ultimately, a race for the survival of technological civilization. Cycle 25 has made it clear that this is not a distant concern, but an imminent reality. The further humanity advances toward a globally interconnected future, the more urgent it becomes to shield our infrastructures against the whims of a star that, while sustaining life, is also capable of collapsing our modern world in a matter of hours. To understand the behavior of the Sun and anticipate the risks its activity may bring to Earth, humanity has built a network of solar observatories that act as permanent sentinels of space. Among the most important are the Solar and Heliospheric Observatory, the Solar Dynamics Observatory, the Parker Solar Probe, and the Solar Orbiter. These instruments are not merely sophisticated telescopes, but true cosmic watchtowers, strategically positioned to observe the star in different wavelengths, record its magnetic activity, and study the solar wind at its origin. In the context of Solar Cycle 25, these observatories have become key tools for understanding why this cycle has exceeded expectations and continues to produce storms of unexpected intensity. The Solar and Heliospheric Observatory, launched in 1995 as a collaboration between the European Space Agency and NASA, is one of the longest operating space observatories still active. Positioned at a stable gravitational point between Earth and the Sun, known as the Lagrange Point 1, the Solar and Heliospheric Observatory has the ability to continuously monitor the solar corona, and detect coronal mass ejections in real time. Thanks to this mission, the first global alert systems for solar storms were established, allowing energy companies, airlines, and satellite operators to prepare hours in advance. The Solar Dynamics Observatory, launched in 2010, brought a revolution in the observation of the photosphere and the chromosphere. Equipped with ultra-high-resolution cameras, it constantly monitors the solar disk in multiple wavelengths, recording in detail sunspots, flares, and changes in the star's magnetic structure. Its images, often shared with the public, reveal the sun in vibrant and dynamic colors, enabling not only cutting-edge scientific studies, but also bringing the reality of space weather closer to the global population. The Parker Solar Probe, launched in 2018, represents an even greater milestone. It is the first spacecraft to approach directly into the solar corona, reaching less than 10 million kilometers from the sun's visible surface, an unprecedented distance. Protected by a state-of-the-art thermal shield, Parker crosses regions of extreme heat to directly measure the solar wind and study the mechanisms that heat the corona to temperatures above 1 million degrees Celsius. Its data are helping to solve mysteries that have intrigued scientists for decades, such as the origin of high-speed energetic particles and the physics behind coronal mass ejections. The Solar Orbiter, launched in 2020 as a partnership between the European Space Agency and NASA, complements this work by capturing images of the sun from never-before-seen angles. Unlike other observatories, the Solar Orbiter can observe high-latitude regions, close to the solar poles, which are fundamental to understanding the dynamics of magnetic cycles. This unprecedented perspective is essential for explaining how the poles invert during solar maximum, and how this influences the approximately 11-year periodicity. Together, these observatories form a network that allows scientists to track solar activity in real time, from the corona's core to the propagation of the solar wind through interplanetary space. Thanks to them, the scientific community can issue increasingly fast and detailed alerts, as well as build models that project the intensity of storms. Although great margins of uncertainty remain, the presence of these spacecraft in space represents a giant leap in Earth's protection against space weather. In Solar Cycle 25, the combined data from the Solar and Heliospheric Observatory, the Solar Dynamics Observatory, the Parker Solar Probe, and the Solar Orbiter became indispensable for explaining the phenomena of 2024 and 2025, when auroras were seen at unprecedented latitudes. They demonstrated that, even with all technology, the sun continues to surprise us, but also that each new cycle is an opportunity for learning. These observatories are, therefore, humanity's eyes fixed on the star that governs our destiny, allowing us to admire its beauty while striving to understand and shield ourselves from its unpredictable fury. Tracking coronal mass ejections is one of the most critical tasks of solar monitoring, as these gigantic clouds of charged plasma are the main drivers of geomagnetic storms capable of affecting Earth. The space telescopes dedicated to this function use special instruments called coronagraphs, which artificially block the intense light of the solar disk, allowing only the corona to be observed. In this way, structures normally invisible become perceptible, and it is possible to follow in real time the birth and propagation of ejections. The Solar and Heliospheric Observatory, in operation since 1995, was a pioneer in this type of observation, recording thousands of events that helped build an essential catalogue for space weather forecasting. When a coronal mass ejection is detected, telescopes measure its speed, sees directions, and density. The speed is calculated by analyzing the expansion of the cloud in sequential images, allowing estimates of how many hours or days it will take to reach Earth. The direction is determined by the position of the event on the solar disk and the shape of the ejection, which may be projected into space in various directions, or, in the most dangerous case, directly toward us. The density of the ejection, inferred from the intensity of the captured brightness, indicates the number of particles in the cloud. These three factors combined are used to calculate the potential for geomagnetic impact. In addition to coronagraphs, space telescopes are equipped with particle detectors and irradiometers that record the sudden increase in radiation and the flux of energetic particles shortly after a solar eruption. These measurements help distinguish between flares, which are pulses of radiation, and coronal mass ejections which carry plasma and magnetic fields. When both occur together, the risks to Earth increase considerably, and tracking becomes even more urgent. Missions such as the Camp Solar Dynamics Observatory provide detailed images of the eruption's point of origin, while probes such as the Epparka Solar Probe directly measure the properties of the solar wind before it reaches our planet. One of the major recent advances in tracking has been the use of multiple observatories in different positions in space, allowing the same ejection to be observed from different angles. This resolves a long-standing limitation. When an ejection is launched toward Earth, the frontal view may make it difficult to measure its actual width and speed. By combining data from satellites in different orbits, it is possible to reconstruct the three-dimensional structure of the cloud and more accurately predict its effects. The solar orbiter, for example, by observing polar and high-latitude regions, complements the frontal view of the Solar and Heliospheric Observatory and the Solar Dynamics Observatory, offering a more complete perspective on solar dynamics. Despite all this equipment, great uncertainties still remain. In many cases, an ejection that appeared weak in images can produce severe storms if its magnetic orientation is particularly unfavorable to Earth. On the other hand, visually impressive ejections can pass almost unnoticed if they are not aligned with Earth's magnetic field. This unpredictability is one of the reasons why space weather remains an evolving field, where each new solar cycle serves as a natural laboratory for learning. In Solar Cycle 25, space telescopes were fundamental in tracking the events of 2024 and 2025, when auroras were seen in unlikely locations. The early detection of these ejections made it possible to issue alerts hours in advance, enough for airlines to reroute flights, satellite operators to activate safety protocols, and power grids to adjust their loads to prevent greater damage. These cases showed that although forecasting is still far from perfect, space telescopes represent the front line of humanity's defense against solar storms. Thus, tracking coronal mass ejections is more than a scientific exercise. It is a matter of global security. Space telescopes are our eyes fixed on the star that sustains life, allowing not only the contemplation of its beauty, but also the anticipation of its moments of fury. In the final sigh of Solar Cycle 25, they continue to play a vital role, helping transform data into protection and science into survival. While billions of people look up at the sky in awe, watching auroras color unlikely horizons, there is a community of scientists living in a different reality, that of the permanent surveillance of the sun. They are the Sigh space weather researchers, men and women working in monitoring centers scattered across the world, following in real time every eruption, every coronal mass ejection, and every variation of the solar wind. The daily lives of these professionals combine cutting-edge science with constant tension, since any alert may mean immediate risk for satellites, power grids, and global communication systems. Their routine begins with the continuous analysis of data sent by satellites such as the Solar and Heliospheric Observatory, the Solar Dynamics Observatory, the Solar Orbiter, and the Epparka Solar Probe. These instruments transmit images, graphs, and measurements almost without pause, creating a direct line between the heart of the Sun and control stations on Earth. Every change in sunspots, every pulse of extreme ultraviolet radiation, or every anomalous particle flow is recorded, interpreted, and reported. The work demands uninterrupted attention because a coronal mass ejection can cover the 150 million kilometers that separate us from the Sun in less than 2 days, leaving little time to prepare defense protocols. The challenge is not only to observe but also to interpret the two. Many times the data arrives mixed with noise, and not every solar eruption results in a significant storm. It is up to the scientist to decide whether the event is worthy of a global alert or whether it can be classified as harmless. This decision-making process is critical, as a false alert may generate panic and economic losses, while the absence of an alert in the face of a real event may result in failures on a planetary scale. It is a delicate balance between prudence and responsibility, where every minute counts. The pressure increases during intense storms, when laboratories and forecasting centers operate under emergency conditions. The Space Weather Prediction Center of the National Oceanic and Atmospheric Administration, for example, operates 24 hours a day, with teams working in shifts to guarantee continuous vigilance. During the events of May 2024, the monitoring room turned into a true crisis center, with specialists issuing reports every hour and coordinating information with airlines, power companies, and governments. In this context, the space weather scientist becomes a key piece in maintaining order in the face of the sun's fury. But the lives of these researchers are not only about tension, there is also the fascination of discovery. With every new piece of data collected, they advance the understanding of solar physics and help build a science that is still expanding. Many report that despite the pressure, it is inspiring to know that their work protects billions of people and at the same time contributes to unveiling the secrets of a star that still holds many mysteries. There is also the satisfaction of taking part in historic moments, such as the auroras at low latitudes that marked solar cycle 25, witnessed not only as cultural phenomena, but also as scientific data of enormous value. In essence, space weather scientists live between two worlds, that of beauty and that of risk. While the population celebrates the lights in the sky, they see the graphs that reveal the cost of these auroras, satellites in danger, grids under threat, and storms that could turn into disasters. Their mission is to turn the unpredictable into something understandable, to gain precious minutes of preparation, and to translate the language of the sun into alerts that can save infrastructures and lives. Thus, the lives of these researchers are a portrait of the human condition before the cosmos, vulnerable yet persistent, fragile yet determined to understand and resist. In the final sigh of solar cycle 25, these guardians of space weather remain on alert, tirelessly watching the star that is both our greatest source of life and our greatest invisible threat. Auroras have always had a profound impact on human imagination. Long before modern science explained their origin, ancestral peoples already sought to interpret the luminous curtains that appeared in polar skies. For Nordic communities, for example, auroras were signs of battles fought between gods and warriors in invisible worlds. Indigenous peoples of North America saw the lights as manifestations of ancestral spirits dancing in the sky, while in Japan, it was believed that conceiving a child under the glow of auroras would bring blessings of luck and prosperity. These narratives reveal the spiritual and symbolic character that the phenomenon assumed in different cultures, always associated with something extraordinary that went beyond everyday understanding. With the advancement of science and the consolidation of the physical explanation for auroras, the fascination did not disappear. On the contrary, it gained new dimensions. If once the mystery lay in the supernatural, now it resides in the grandeur of cosmic physics. Knowing that particles launched at millions of kilometers per second by the sun are guided by Earth's magnetic field and illuminate the sky with vibrant colors only reinforces the perception that we live on a planet intimately connected to the cosmos. In this sense, science did not replace myth but gave it a new form, transforming the phenomenon into a scientific and cultural spectacle. In the digital age, auroras have also migrated to the heart of global popular culture. The images captured in May 2024 and in 2025 went viral on social media, reaching billions of views in just a few days. Platforms such as Instagram, TikTok, and YouTube were flooded with videos of illuminated skies in unexpected places, while hashtags related to the phenomenon quickly entered the world's trending topics. The result was a true cultural fever. Millions of people who had never seen an aurora began to actively seek it out, installing applications that monitor the KP index, following aurora forecasting pages, and planning trips to polar regions. The media impact was so great that the phenomenon went beyond amateur astronomy and reached the entertainment and tourism markets. Documentaries, series, and films began to include auroras as visual symbols of cosmic connection and transcendental beauty. Tourism companies recorded a significant increase in demand for trips to regions such as Iceland, Norway, and Alaska, where the probability of seeing the spectacle is high. At the same time, locations in mid and even low latitudes began to be valued for the possibility, albeit rare, of witnessing the phenomenon under exceptional conditions. Another curious aspect of the popularization of auroras is their contemporary psychological and spiritual impact. For many people, Watching the phenomenon is not just contemplating a display of lights, but living a transformative experience. There are reports of individuals who describe auroras as moments of connection with the universe, capable of awakening feelings of humility, belonging, and even personal renewal. This subjective dimension, amplified by social media, has made auroras symbols of the fragility and grandeur of human life in the face of the cosmos. In the context of solar cycle 25, auroras ceased to be isolated phenomena in remote regions and became part of a global collective memory. In 2024 and 2025, billions of people were able to see, record, or at least share images of the phenomenon, transforming it into a cultural event of unprecedented scale. This interweaving of science, ancestral myth, and digital culture shows how auroras continue to occupy a central place in human imagination, being at once a physical spectacle and a spiritual experience. Thus, auroras represent the union between past and present, between myth and science, between the local and the global. From the fire of the gods in Nordic skies to the fever of likes and shares on social media, they remain universal symbols of admiration and mystery. In the final sigh of solar cycle 25, this cultural fusion will continue to expand, reinforcing the power of auroras not only as a natural phenomenon, but as part of the collective identity of humanity in the face of the sun. With the popularization of auroras as both a cultural and scientific phenomenon, a steadily growing market has emerged: aurora tourism. For decades, traveling to observe this spectacle was a privilege restricted to adventurers or scientists who ventured into polar regions, often under extreme conditions of cold and isolation. Today, however, thousands of people plan their vacations exclusively around the chances of witnessing the phenomenon, turning places like Iceland, Norway, Sweden, Finland, Canada, and Alaska into true tourist hubs during winter. This interest grew even more after the superstorms of 2024 and 2025, when millions of people witnessed auroras in unexpected latitudes and began dreaming of experiencing them in regions where the spectacle is almost guaranteed. Specialized tourism agencies offer complete packages that include stays in glass cabins, transparent igloos, and even luxury hotels designed to maximize sky views. In countries like Finland, it is common for visitors to stay in structures with heated glass roofs, allowing them to watch the dancing curtains of light directly from bed in thermal comfort. In Iceland, nighttime jeep safaris traverse remote areas away from light pollution in search of the best observation points. In Canada and Alaska, special flights offer the chance to watch auroras above the clouds, ensuring a clear view even on cloudy nights. Aurora tourism is not limited to the northern hemisphere. In Antarctica, cruises and scientific expeditions open space for visitors willing to face the most extreme conditions in exchange for glimpsing the southern aurora. Though more difficult and expensive, this type of trip represents the pinnacle of aurora tourism, combining science, adventure, and cosmic contemplation. For some, observing the phenomenon in both hemispheres has become a life goal, almost like a modern pilgrimage in search of the rarest and most spectacular natural beauty on the planet. This tourism growth, however, also raises environmental and cultural questions. In many polar regions, the increased flow of visitors puts pressure on local communities and fragile ecosystems. Infrastructure must adapt to receive tourists on a large scale, and there is the risk of undermining traditional cultures due to international demand. At the same time, there are significant economic benefits. Cities that once depended on fishing or mining have found in aurora tourism a new source of sustainable income, capable of generating jobs and revitalizing local economies. Another curious aspect is the impact of technology on aurora tourism. Today, real-time forecasting applications provide information on the intensity of the KP index and the likelihood of auroras occurring in a given region. This allows tourists to adjust their trips almost like checking the weather forecast. The spread of high-sensitivity cameras has also changed the way the phenomenon is experienced. Even when the human eye sees only a faint glow, modern lenses reveal vibrant colors that make the experience even more spectacular. Solar Cycle 25 propelled this market to unprecedented levels after the records of 2024 and 2025 at low latitudes Millions of people became interested in traveling to places where auroras are recurring. The surge was so significant that airlines created seasonal routes specifically for auroral destinations, while digital platforms began offering thematic packages focused on the phenomenon. This tourism boom demonstrates how the beauty of the sun and its interaction with Earth has been transformed into a cultural and economic product, capable of uniting science, leisure, and spirituality. Thus, aurora tourism reveals one of the most fascinating aspects of humanity's relationship with the cosmos, our willingness to travel to the ends of the Earth to witness the luminous dance of solar particles in Earth's atmosphere. It is the modern translation of an ancestral desire to connect with the universe, now driven by airplanes, hotels, and applications. In the final Sigh of solar cycle 25, this movement is expected to grow even further, consolidating auroras as one of the greatest natural spectacles human beings can seek. The fascination with auroras has not only transformed the way people look at the sky, but it has also created a global economic market around the phenomenon. Tourism associated with auroras moves billions of dollars every year, involving airlines, travel agencies, hotels, restaurants, local guides, and even the photographic equipment industry. The exponential increase in searches and bookings for polar destinations after the events of 2024 and 2025 made it clear that solar cycle 25 not only brought new auroras to low latitudes, but also fueled an entire economy built around the experience of watching the luminous spectacle of the sun interacting with Earth. The impact is evident in regions traditionally associated with aurora tourism, such as Iceland, Norway, Finland, Sweden, Canada, and Alaska. Hotels specializing in sky observation recorded maximum occupancy, and transport companies had to expand the availability of packages. In some countries, aurora tourism has come to represent a significant share of the regional gross domestic product, sustaining local economies that once depended solely on fishing, mining, or livestock. This movement brought jobs, infrastructure development, and business opportunities to areas previously considered remote and economically isolated. In addition to recreational tourism, a scientific tourism associated with auroras has also emerged. Universities and research centers organize expeditions that combine science outreach with practical experience, allowing students and enthusiasts to learn about the sun, the magnetosphere, and space weather directly in the field. This type of educational tourism strengthens the public perception of science and generates additional income for local communities. In some cases, volunteer programs allow tourists to assist in measurements and observations, turning travelers into collaborators in scientific research. The equipment market has also been boosted by the popularity of auroras. High-sensitivity cameras, lenses specifically designed for astrophotography, and even drones adapted to capture night images have seen a significant increase in sales. Digital platforms, in turn, profited from live broadcasts of the phenomenon, monetizing channels that streamed auroras in real time to millions of viewers. Even the fashion and design sector was influenced, with products inspired by auroral color palettes, ranging from clothing and accessories to interior decoration. A curious fact is that the aurora craze also affected the real estate sector. In some Scandinavian cities, there was a growing interest from foreigners in acquiring houses or cabins in regions with high aurora probability, transforming the natural phenomenon into a factor of real estate appreciation. This movement reinforces the long-term economic impact, which goes beyond tourist seasons and integrates into the social and financial dynamics of communities. In solar cycle 25, this aurora economy was intensified by digital virality. Images that became global trends on Google Trends and social networks created a cascading effect. The more people saw them, the more they wanted to travel, and the more tourists arrived, the more the industry expanded. This chain reinforces how science, culture, and economy are interconnected in a cycle that turns cosmic phenomena into drivers of human development. Thus, the economic impact of auroras shows that they are much more than a visual spectacle. They are also a natural resource converted into tourist experience, cultural product, and even international marketing strategy. The final Sigh of solar cycle 25 will not only continue to produce lights in the sky, but also sustain an entire global economic network fueled by humanity's fascination with this spectacle that unites Earth and Sun. The advancement of digital technology has brought space weather into the daily lives of millions of people around the world. If in the past, only specialized scientists had access to data about the solar wind, coronal mass ejections, and the KP index, today mobile applications and digital platforms offer real-time forecasts accessible to any user. This democratization of information has turned aurora monitoring into a common practice, similar to checking the weather forecast to decide whether to bring an umbrella. The phenomenon, which was already spectacular in itself, has become even more integrated into people's lives through alerts, maps, and graphs that anticipate the possibility of seeing dancing lights in the sky. Aurora forecast applications use data from solar observatories, such as SOHO, SDO, Parker Solar Probe, and Solar Orbiter, as well as measurements from global magnetometer networks to calculate in real time the intensity of geomagnetic storms. From this information, maps are generated showing at which latitudes the phenomenon is likely to be observed. Many applications include personalized alerts that send notifications whenever the KP index reaches high values, allowing enthusiasts to immediately go outside to observe the sky. In some cases, even drones and automated cameras are integrated into these systems, capturing images and streaming them live to online communities. This easy access has given space weather a cultural character. Ordinary people without training in physics or astronomy have become familiar with technical terms such as KP index, geomagnetic storm, or coronal mass ejection. In May of 2024 and 2025, when auroras lit up skies in tropical regions, downloads of these applications skyrocketed. Platforms such as Google Trends recorded historic peaks in searches for the term Northern Lights, and social networks were filled with posts accompanied by screenshots showing forecasts and real-time graphs. Collective interest turned space weather forecasting into a shared and participatory experience. The democratization of access has also brought scientific benefits. Many applications encourage users to submit aurora observation reports, which are integrated into global databases. This has created a form of citizen science, where thousands of testimonies help researchers confirm models, validate forecasts, and even identify storms that might otherwise go unnoticed by observatories. This flow of decentralized information enriches the work of scientists and brings the public closer to the research universe. However, this popularization also presents challenges. Not all applications provide scientifically accurate information, and in some cases, simplified forecasts may create false expectations or misinterpretations. This requires official agencies, such as NASA and NOAA, to reinforce public communication by providing accessible data without compromising scientific rigor. The balance between clarity, accuracy, and popularity is essential for the democratization of space weather to be a tool for education and preparedness, and not just entertainment. In Solar Cycle 25, forecast applications became an inseparable part of the cultural experience of auroras. In middle and low latitudes, where the phenomenon is rare, millions of people began to rely on these alerts so as not to miss the chance to witness a historic spectacle. This integration between science, technology, and daily life represents a paradigm shift. The sun, once observed only through telescopes and by scientists, is now monitored in real time by anyone with a mobile phone in their pocket. Thus, the popular forecasting of auroras symbolizes the era we live in, a time when cosmic data circulates as widely as information about terrestrial weather. In the final sigh of Solar Cycle 25, this democratization will continue to bring humanity closer to the sun, transforming complex phenomena into shared experiences and reinforcing the perception that, even in the face of an immense cosmos, we are all connected by the same star. The cultural impact of auroras in Solar Cycle 25 cannot be understood without considering the central role of social media and search engines. In May of 2024, when the first superstorms brought luminous curtains to the skies of mid and even tropical latitudes, digital platforms were flooded with videos and photographs of the phenomenon. The result was immediate, a global boom of interest, clearly measured by Google Trends, which recorded the highest peak in history for searches of the term Northern Lights. This surge was not only a reflection of collective fascination, but also a milestone showing how the digital era has transformed natural phenomena into mass cultural events. In the past, auroras at low latitudes might have been recorded in diaries, local newspapers, or isolated reports. Today, every occurrence turns into a global spectacle shared in real time. Users in Brazil, Mexico, Spain, or regions of Africa posted videos on TikTok and Instagram that reached millions of views within hours. Hashtags related to the phenomenon trended on Twitter, and live streams by aurora chasers attracted global audiences. This instant viralization amplified the cultural impact of Cycle 25, turning each aurora into a collective event that united different countries and languages around a single visual experience. Google Trends became a curious tool to measure this fever. The graphs showed that with every new solar storm, there was an explosion of searches not only for northern lights, but also for technical terms, such as KP index, solar storm, and space weather. This indicates that the interest was not limited to the visual spectacle, but expanded to a search for scientific knowledge. Millions of people began exploring websites of NASA, NOAA, and specialized portals, boosting scientific outreach and bringing the population closer to concepts that had once been restricted to laboratories and universities. The role of social media was even deeper. By turning the phenomenon into shareable content, they democratized access to the aurora experience. Even those who never witnessed the phenomenon in person could feel part of the global event by watching videos, joining live streams, or interacting in comments. This collective experience amplified the cultural meaning of auroras, transforming them into symbols of the digital age. More than ever, the phenomenon ceased to be local and became global, integrating itself into the collective memory of billions of people. In addition, the viralization of auroras generated immediate economic impacts. The surge in searches was accompanied by an explosion of interest in aurora tourism, in the purchase of astrophotography cameras, and even in clothing and products inspired by the colors of the phenomenon. Google Trends, therefore, not only reflected public curiosity, but also anticipated market movements that benefited entire sectors of the economy. The search boom also served as a reminder that the internet is today the great stage of integration between science, culture, and economy. Natural phenomena, once restricted to the gaze of a few, become part of the global collective experience within minutes. In Cycle 25, auroras were not only lights in the sky, but catalysts of a cultural revolution mediated by digital networks. Thus, the case of auroras in Google Trends shows how humanity, in the 21st century, translates cosmic wonders into clicks, likes, and online searches. It is a reflection of our era. Celestial phenomena that cross continents end up being recorded not only in individual memory, but also in algorithms that map global interests. In the final sigh of Cycle 25, every new aurora will continue to generate not only admiration in the sky, but also digital waves echoing across the entire planet. Auroras are not only physical phenomena or luminous spectacles in the sky. They carry with them a deep psychological and spiritual force, capable of transforming the way people perceive themselves and the world around them. When millions of solar particles collide with the atmosphere and create colored curtains of light that dance silently on the horizon, the impact goes far beyond vision. It reaches emotions, memories, beliefs, and even spirituality. The fascination with this phenomenon transcends cultures, generations, and historical contexts, showing that, in essence, human beings respond to auroras in a universal way, with admiration, reverence, and a sense of connection with something greater. From a psychological perspective, observing an aurora provokes a state close to what researchers call an awe experience. It is a moment in which the mind is taken over by something so vast and beautiful that it defies rational understanding. This type of experience is associated with a reduction in egocentrism, an expansion of the sense of belonging, and the strengthening of social bonds. Studies show that people exposed to awe experiences tend to develop more empathy, gratitude, and a sense of community. Auroras, therefore, are not only natural spectacles, but also catalysts of positive and transformative mental states. There is also the spiritual aspect. In different cultures, auroras have been interpreted as divine manifestations, signs from ancestors, or messages from other worlds. In the present, even in highly technological societies, Many people report feeling a kind of transcendence when witnessing the phenomenon. The silence of the night, interrupted only by the dance of the lights, invites contemplation and the sense that we are part of a larger cosmic reality. Some describe the experience as a silent prayer, others as an intimate encounter with the universe. This spiritual impact helps explain why so many people, when seeing auroras for the first time, are moved to tears. Social media has amplified this psychological aspect. By sharing images and accounts, individuals find validation for their feelings, creating a global community connected through the collective experience. Comments on viral videos often mention words such as incredible, divine, magical, or spiritual. This language reflects how, even in a scientific context, auroras continue to be perceived as something that transcends logic. At the same time, massive dissemination allows millions of people who have never seen the phenomenon in person to feel part of this collective emotional experience. In Cycle 25, the psychology of auroras gained prominence because the phenomenon was no longer restricted to polar latitudes and reached entire populations in tropical regions. For these people, the surprise of seeing the sky lit up with impossible colors amplified the emotional impact even more. It was not only about contemplating a natural beauty, but about experiencing something that seemed impossible within their cultural horizon. This break in expectation intensified the emotion, leading many to describe the phenomenon as a once-in-a-lifetime moment. Thus, auroras reveal how much nature has the power to shape not only the physical landscape, but also the inner landscape of human beings. They remind us of our smallness in the face of the cosmos, but also of our ability to feel, reflect, and find meaning in phenomena that surpass us. In the final sigh of Cycle 25, each new aurora will continue to be not only a spectacle for the eyes, but also a psychological and spiritual experience that connects humanity to the star that governs its existence. Faced with the advance of solar storms in Cycle 25 and the growing vulnerability of modern society, governments, scientists, and private sector companies have begun to discuss and implement global preparedness strategies. The risk of an event similar to Carrington in the 21st century has ceased to be just an academic hypothesis and has become a practical concern of national security and even planetary security. This preparedness involves technological defense protocols, public policies for resilience, and an international network of monitoring and scientific cooperation. In the governmental sphere, some countries already treat space weather as a strategic issue. The United States, for example, maintains the Space Weather Prediction Center of the National Oceanic and Atmospheric Administration, which operates full-time and issues official solar storm alerts. The European Union coordinates efforts through the European Space Agency, which provides reports and protocols for its member states. Other nations, such as Japan, Canada, and Australia, also have their own monitoring centers, integrated into a global cooperation network. This joint work is essential because a solar storm knows no borders. Its effects strike the entire planet simultaneously. Science plays a central role in this preparedness process. Space missions such as Parker Solar Probe, Solar Orbiter, and observatories such as SOHO and SDO provide data that feed predictive models. These models help estimate the speed, density, and direction of coronal mass ejections, allowing alerts to be issued hours in advance. Although this time margin is small, it is enough for airlines to divert polar routes, satellite operators to activate protection protocols, and energy companies to reduce loads on transmission lines to avoid overloads. Every minute gained through forecasting represents billions of dollars in avoided losses and, above all, lives preserved. In the technological sector, private companies are also developing defense protocols. Satellite internet companies have created systems that automatically shut down more vulnerable equipment during severe storms. Power grid operators are investing in more resistant transformers and in devices that block induced currents. Even aviation has begun adopting pre-planned alternative routes for periods of high solar activity. These measures reflect a growing awareness that space weather must be treated as an inevitable risk, not as a distant possibility. At the same time, global preparedness requires public education and communication. Many countries already include emergency protocols in their civil defense manuals, instructing the population on how to act in case of prolonged blackouts or loss of communications. Although these scenarios are still rare, preventive preparation avoids panic and increases social resilience. In 2024 and 2025, the episodes of auroras at low latitudes helped popularize the subject, bringing people closer to the idea that the sun is not only a source of light, but also a risk factor for modern life. Despite all these efforts, experts recognize that global preparedness is still uneven. Developing countries with fewer resources to invest in technological and scientific infrastructure remain more vulnerable. This means that, in the event of an extreme event, the impacts would be felt disproportionately, widening already existing inequalities. This reality reinforces the need for international cooperation, not only scientific, but also political and economic, so that defense protocols can be shared and applied on a planetary scale. Thus, global preparedness against solar storms is not only a matter of science or technology, but of collective survival. Cycle 25 has shown that the sun remains an unpredictable force, capable of directly affecting civilization. Ensuring that governments, companies, and citizens are prepared means turning knowledge into resilience and science into protection. In the final sigh of this turbulent cycle, every preparedness measure is a step toward a safer future under the light and the fury of our star. Every solar cycle has a peak moment, followed by a period of slowdown, in which the activity remains intense but tends to gradually decrease until the arrival of the next solar minimum. This transition period is called by many specialists the final sigh, a phase marked by unpredictable storms, powerful coronal mass ejections, and auroras that can surprise even when solar activity is expected to decline. In the case of Cycle 25, which reached its peak around the middle of 2025, scientists project that this final sigh will extend until approximately the year 2027, bringing another 2 years of strong cosmic turbulence. During this phase, the Sun continues to release significant energy, the result of the instability generated by the inversion of its magnetic poles, a phenomenon that occurs every 11 years. Although the number of sunspots tends to gradually decrease after the maximum, each of them can still give rise to intense flares and coronal mass ejections capable of impacting Earth. This means that even with the forecast of declining activity, the risks remain high and can generate storms comparable to the greatest ever recorded. The history of previous cycles shows that some of the most destructive events happened precisely during this final period, when the Sun seems to breathe before entering rest. Between 2025 and 2027, specialists expect that there will still be several severe geomagnetic storms. This means that the probability of new auroras at middle and low latitudes will continue to be present, fueling the global expectation of witnessing the phenomenon again. At the same time, satellites, power grids, and communication systems will need to keep defense protocols active, since any carelessness could result in large-scale failures. The experience of May 2024 and the waves of 2025 serve as a warning that the vulnerability of modern civilization remains evident. From a scientific point of view, the final sigh of Cycle 25 will be a valuable opportunity to consolidate the knowledge accumulated with recent observations. The Parker Solar Probe and Solar Orbiter missions, which are still ongoing, will provide crucial data to understand how the solar corona generates these late storms. At the same time, ground-based observatories such as the Daniel K. Inouye Solar Telescope are expected to record detailed images of the remaining sunspots, helping to improve predictive models for the next cycle. This period will therefore be a living experimental field for space weather science. Culturally, the final sigh promises to keep alive the fever for auroras. Populations around the world, who already had the privilege of seeing the sky lit up in vibrant colors during 2024 and 2025, will remain on alert, following apps, forecasts, and live broadcasts. It is likely that new episodes will once again reach countries at low latitudes, reinforcing the collective feeling that we are living in a special era in which the Sun is closer to popular imagination than ever before. Thus, the final sigh of Cycle 25 will be an intense transition phase, both for science and for culture. It will remind us that solar activity is cyclical, but also unpredictable in its details. Between 2025 and 2027, we will continue to live under the expectation of new storms, new auroras, and new lessons. The sun, in its last exhalation before the next rest, will keep Earth in suspense, divided between the wonder of the lights in the sky and the vigilance necessary to protect civilization from its overwhelming force. Solar Cycle 25 will be remembered as one of the most surprising of the modern era. Initially predicted to be a cycle of moderate intensity, it defied expectations and delivered geomagnetic storms that colored the skies of mid and even tropical latitudes, spreading auroras to regions where they had never before been seen by so many people. These episodes not only transformed the phenomenon into a global spectacle, but also into a collective memory, marked by billions of digital records, historic online searches, and the explosion of popular interest that united science and culture on a planetary scale. The cultural impact was profound. Peoples who had never had contact with auroras began to witness them in their own skies, reinforcing the feeling that we are living in extraordinary times. Social networks amplified this experience, transforming local events into global phenomena, capable of mobilizing collective feelings of admiration, belonging, and even spirituality. Google Trends recorded search records, while aurora tourism expanded like never before, proving that the beauty of the sky can be translated into economic, cultural, and scientific movement. But Cycle 25 was not only a spectacle, it also served as a warning of the vulnerability of modern civilization. Satellites suffered failures, navigation systems presented errors, power grids had to activate emergency protocols, and airlines diverted routes to protect passengers from radiation. Each bright aurora was at the same time a sign of risk, a reminder that the sun remains an uncontrollable cosmic force, capable of compromising in minutes the technologies on which human life has become dependent. The lessons from this cycle reinforced the need for international cooperation, scientific advances in forecasting, and investments in more resilient infrastructure. The final Sigh, projected to extend until 2027, still promises new waves of instability. Unexpected auroras, severe storms, and valuable lessons will continue to emerge, keeping the sun at the center of scientific and cultural attention. However, it is already possible to state that Cycle 25 marked a turning point in the relationship between humanity and space weather. Never before had so many people been aware that we live on a planet profoundly connected to the activity of its star. Thus, the collective memory of Cycle 25 will be twofold. On one hand, remembered as the era when billions of eyes turned to the sky to witness the spectacle of auroras in vibrant colors. On the other, as the moment when governments, scientists, and societies realized that they must prepare to face the risks of superstorms. This duality between wonder and vulnerability will be the legacy of Solar Cycle 25, a cycle that showed us, with beauty and with risk, that the sun continues to be the silent and powerful protagonist of Earth's history. We have reached the end of this long journey through Solar Cycle 25, its storms, auroras, and mysteries. We have seen how the sun, in its phase of maximum activity, transformed the sky into a global spectacle, but also reminded us of the fragility of our technologies in the face of its power. Each aurora, each solar explosion, and each impact report were chapters of a story that united science, culture, and collective memory. Now, as we move toward the final Sigh until 2027, we remain expectant before the star that governs our existence. If this content helped you to better understand how the sun influences our lives and awakened your fascination for auroras and space weather, take this moment to strengthen our community. Subscribe to the channel, activate the notification bell to receive the next episodes, and leave your like because this helps us bring this knowledge to more and more people. And I want to know from you, where are you watching from? Write in the comments your city, your country, and tell us if you have already had the opportunity to see an aurora with your own eyes, or if you dream of witnessing this spectacle one day. Let us create together a global map of people connected by the same sky, the same sun, and the same cosmic fascination. Thank you very much for staying until the end. I wish you a peaceful night of learning and contemplation. May the next auroras, real or imagined, always bring the reminder that we are part of a vast and vibrant universe, in which the sun is at the same time source of life, spectacle, and challenge. Until the next episode, and sweet dreams.